Telescope James Webb just picked up something that shouldn't be possible. 40 light-years away, orbiting a dying red dwarf star, there's a planet, and I mean, there's a real, actual planet that might be the closest thing to Earth we've ever found outside our solar system. But here's where it gets wild. This planet, TRAPPIST-1e, gets hammered by solar flares roughly every 2 days. Every 2 days. To put that in perspective, the most catastrophic geomagnetic storm to ever hit Earth was the Carrington event back in 1859. That nearly destroyed our entire civilization. We're talking knocked out telegraph systems worldwide, auroras visible at the equator, compasses going haywire. Scientists classified that as a greater than 1 in a 100-year event. On TRAPPIST-1e, that level of solar fury happens on a Tuesday, then again on Thursday, and again on Saturday. So how could anything possibly survive there? How could an atmosphere even exist? And yet the data from James Webb is suggesting something extraordinary, something that honestly feels like it shouldn't be real. This is the first time we've had genuine evidence of what looks like a secondary atmosphere on an exoplanet. Not speculation, not models, actual observational data from the most powerful space telescope ever built. Welcome to the story of how we might have just found our closest neighbor in the universe, and why that neighbor might be home to something we've been searching for our entire existence. My name's Alex, and what we're about to dive into is genuinely one of the most mind-bending discoveries of the past decade. I'm not going to waste your time with flowery language or drawn-out introductions. You're here because you want to know if we've actually found a second Earth. You want to understand how this is even possible, and by the end of this video, you're going to have a real solid understanding of what James Webb found, why it matters so much, and what the next steps actually are. Let me be straight with you though, this isn't a done deal. We're not popping champagne bottles at NASA just yet. There are real complications here. There are mysteries that make this whole thing seem almost impossible. But that's exactly what makes it so fascinating. Because science isn't about certainty, it's about asking the right questions and following the data wherever it leads, even when that data points somewhere wild. The James Webb Space Telescope is fundamentally different from every telescope we've ever built before it. We're not talking about incremental improvements. We're talking about a complete paradigm shift in how we observe the cosmos. Where Hubble could barely resolve individual stars in distant galaxies, Webb can look at the atmosphere of a planet orbiting those stars. It can detect the chemical fingerprint of gases in an alien sky. It can tell us what's happening on worlds we'll never physically visit. And about 6 weeks ago, the DREAMS team, that's the deep reconnaissance of exoplanet atmospheres through multi-instrument spectroscopy collaboration, used up all their guaranteed observation time on the James Webb Telescope to focus on one specific system, the TRAPPIST-1 system. They already had hints from earlier observations that something interesting was happening around TRAPPIST-1e, so they decided to go all in. They observed 4 separate transits of TRAPPIST-1e crossing in front of its parent star. 4 times this planet passed between us and the star, and each time Webb collected data. The precision was insane. The data they got back was 10 times more sensitive than anything we'd ever gathered from any other exoplanet system. Let me repeat that. 10 times. That's not a marginal improvement. That's revolutionary. And what they found has fundamentally changed how we think about this planet. See, here's the thing about finding Earth-like worlds. It's not just about the planet's size or its mass or where it orbits. Size and mass matter, sure. Distance from the star matters, absolutely. But what really determines whether a planet could support life is whether it has an atmosphere. An atmosphere does so many critical things. It protects you from radiation. It traps heat. It provides the raw materials for chemistry, for weather systems, for the kind of dynamic environment where biology can emerge. For years, scientists looked at TRAPPIST-1e and thought maybe this planet could have made it through. Maybe enough survived the stellar onslaught. But they didn't know. They couldn't know. Not until Webb. And now they have evidence. Not proof. Not certainty. But genuine, credible evidence that TRAPPIST-1e has an atmosphere. That means water could exist there. That means the basic chemistry for life could be happening. That means we might be looking at the first true analog to Earth ever discovered. I want to take you through exactly what that means. I want to show you the data. I want to walk through the logic. But first, you need to understand the system itself, because TRAPPIST-1 isn't like our solar system. It's not like anything we grew up imagining when we thought about space. TRAPPIST-1 is old, incredibly old. We're talking somewhere around 7.6 billion years old. Our sun is only 4.6 billion. That means TRAPPIST-1 was already ancient when Earth was first forming. It's a red dwarf, which means it's small, cool, and it produces most of its energy through nuclear fusion deep in its core. Because it's so efficient at fusing hydrogen, it could theoretically keep burning for 10 trillion years. That's 700 times the current age of the entire universe. Now that sounds great for stability, but here's the problem. Because red dwarfs live so long, their violent, chaotic teenage years are also incredibly long, billions of years. And during those early billions of years, they're throwing around radiation and stellar winds and particle storms like there's no tomorrow. It's not a gentle childhood, it's a hellscape. Eventually, though, they calm down. They settle into what's called the main sequence. That's where TRAPPIST-1 is now. But the damage from those early years, that's permanent. The inner planets have been battered. The outer ones might have held on to something, but you really don't know what. Yet somehow, orbiting this ancient temperamental star, there are 7 planets, 7, all rocky, all roughly Earth-sized. This isn't some theoretical model or computer simulation. These are real planets we've detected through careful observation. We know they're there. When they were first discovered in 2017, it felt like we'd hit the jackpot. 7 potentially habitable worlds around one star. That was unprecedented. But as we learned more, the reality became more complicated. Most of them are probably too hot. One might be okay. And then there's TRAPPIST-1e. TRAPPIST-1e is special because it sits right in the middle of what we call the habitable zone. That's the distance from a star where a planet could theoretically maintain liquid water on its surface, close enough to get warmth, far enough away not to get fried. For TRAPPIST-1a, that works out perfectly. It receives about 2/3 the energy from its star that Earth receives from the sun. That's actually ideal. That could mean a climate similar to Earth. That could mean oceans. That could mean potentially life. But there's a catch, and it's a big one. Because TRAPPIST-1e is so close to its star, 1/13 the distance Mercury is from the sun, it's probably tidally locked. That means one side always faces the star, and one side always faces away. It's like our moon. We only ever see one face of the moon because it's tidally locked to Earth. The same thing happens on TRAPPIST-1e with its star. Now, you might think that sounds terrible for life. One side burning, one side frozen. But here's where it gets interesting. Atmospheric models suggest that if TRAPPIST-1e does have an atmosphere, it could actually transport heat to the dark side. It could create a circulation system that keeps the whole planet habitable. Wind patterns, weather systems, an actual climate. It wouldn't be like Earth, but it might work. That's the theory. That's what the models suggest. But theories and models are one thing. Data is something else entirely. Which brings us back to James Webb. Because James Webb doesn't work like the telescopes we're used to. It doesn't just take pictures. Well, it does, but that's not its superpower. Its real superpower is spectroscopy. It can break down light into its component wavelengths. It can see which colors are being absorbed by different molecules. When TRAPPIST-1e passes in front of its parent star, what we call a transit, the light from the star travels through the planet's atmosphere before reaching us. And as that light passes through, different gases absorb different colors. Carbon dioxide absorbs in certain wavelengths. Water vapor absorbs in others. Methane has its own signature. Nitrogen has another. So when Webb measures which colors of light make it through and which ones don't, it can essentially read the chemical composition of the atmosphere. It's like being able to smell a city from miles away and knowing exactly which factories are running based on the scent. Except instead of smell, we're reading light. Instead of cities, we're reading planets 40 light years away. That's the technology, that's the capability, and that's exactly what the DREAMS team used when they pointed Webb at TRAPPIST-1e. They observed 4 transits, 4 separate times when the planet passed in front of its star. Each observation was meticulous. Each one was squeezed for every possible bit of information. And when they compiled the data, when they looked at what wavelengths were being absorbed, what wavelengths were getting through, they saw something remarkable. They saw evidence of an atmosphere. Now, I want to be careful here because this is where people often get overexcited, and I get it, the headline is thrilling. We found an atmosphere on an exoplanet, but the details matter, because finding an atmosphere and finding a habitable atmosphere are 2 very different things. The data ruled out certain possibilities. There's no dense primordial atmosphere of hydrogen and helium. That would have an obvious signature, and it's not there. There's no thick carbon dioxide atmosphere like Venus. That's also clearly absent. There's no thin, wispy Martian atmosphere. That doesn't match the observations either. What the data actually suggests is something different, something that points toward a secondary atmosphere, an atmosphere that the planet made itself over time, through volcanic outgassing, through the release of gases that were locked in the planet's interior. That's how Earth got its atmosphere, by the way, not through capture or inheritance from the nebula that formed the solar system, but through the slow, steady release of gases from inside the planet. If TRAPPIST-1e has a secondary atmosphere, if it has managed to build up a layer of gases despite the constant bombardment from stellar flares, then we're looking at something genuinely extraordinary, because that would mean the planet didn't just form in the habitable zone, it actively maintained habitability, it fought for it. The most likely composition, based on the current data, is an atmosphere dominated by heavier gases, nitrogen probably, with greenhouse gases like water vapor, carbon dioxide, or methane. An atmosphere with a surface pressure similar to Earth. About 1 bar, that's the pressure you feel right now, standing on Earth's surface. If that's real, if that's actually what's on TRAPPIST-1e, then the planet could maintain liquid water. It could have oceans on the day side, perhaps even a global ocean thanks to atmospheric circulation. The climate would be alien, sure. The stars would look different. The day would never end. But the fundamental chemistry, the basic conditions for life as we understand it, could be present. But here's where we hit the real puzzle. Here's where the whole thing seems almost impossible. How does an atmosphere survive on a planet being bombarded by solar flares every 2 days? That's the question that keeps scientists up at night. Because mathematically, the numbers don't add up. The energy from those flares should be stripping away the atmosphere layer by layer. It should have been gone billions of years ago. The planet should be a naked rock, a barren world with no protection, no climate, no chance. And yet here we are, looking at data suggesting an atmosphere exists. So either the data is wrong, which is possible, or the planet found a way. The planet found a way to keep its atmosphere despite the constant assault. And if that's true, if that's actually what's happening, then we need to understand how. Because if a planet can keep an atmosphere in the face of that kind of stellar violence, then our understanding of which planets could harbor life fundamentally changes. This is where the story gets really interesting. This is where we move beyond just observing data and start asking deeper questions about the nature of planets, of atmospheres, of life itself. But before we get there, before we explore how this planet might actually be surviving this ordeal, you need to understand something crucial. You need to understand that finding an atmosphere on TRAPPIST-1e isn't the end of the story. It's actually the beginning. Because now the real questions start. Is this atmosphere stable? Is it self-sustaining? Could it actually support life? Those are the questions the scientific community is grappling with right now, and the answers might just rewrite everything we thought we knew about where life could exist in the universe. So stick with me. Because what comes next is going to blow your mind. We're going to dig into the actual mechanisms. We're going to explore the possibilities. And we're going to come face to face with something that honestly feels almost like science fiction. A potential second Earth, orbiting a star you can't even see with your naked eye, 40 light years from home. This is real, this is now, and this is absolutely worth paying attention to. Let me walk you through exactly how this detection works, because it's the foundation of everything we're about to discuss. If you understand the mechanism, the rest of the story makes sense. If you don't, well, you're just taking my word for it. James Webb uses something called transmission spectroscopy. The name sounds complicated, but the concept is actually straightforward. When a planet passes in front of its parent star, remember we call that a transit, the starlight has to travel through the planet's atmosphere before it reaches us on Earth. And when light passes through gas, something remarkable happens. Different molecules absorb different wavelengths of light. Think about looking at a city skyline at night through a haze of smog. You can see the lights, but they're muted, filtered. Different types of pollution filter out different colors of light. Smoke scatters blue more than red. Dust absorbs certain wavelengths entirely. The color of the haze tells you something about what's in the air. James Webb does the same thing, except instead of pollution, it's looking for atmospheric gases on exoplanets. And instead of the naked eye trying to figure out why the sunset looks weird, it has impossibly sensitive instruments that can measure the precise wavelengths of light that make it through and which ones get absorbed. Carbon dioxide, it has a specific absorption pattern in the infrared. You measure it. Water vapor, different pattern. Methane, another signature entirely. Each molecule is like a fingerprint. You read the fingerprints in the light spectrum, and you know exactly what's in that atmosphere. The reason James Webb is so incredibly good at this is because it works in the infrared. Our eyes see visible light. Most ground-based telescopes work in visible light. But infrared, that's where the molecular absorption signatures really show up clearly. That's where you get maximum contrast. And the infrared spectrometer on board Webb, called NER-SPEC, can measure these wavelengths with stunning precision. Here's what makes this even more remarkable. TRAPPIST-1 is a very dim star. Most stars we study are bright, which actually makes exoplanet detection harder. When a planet transits a bright star, the change in brightness is tiny. It's like trying to spot a candle in front of a searchlight. But TRAPPIST-1, it's dim, so when TRAPPIST-1e passes in front of it, the relative change in brightness is larger. The planet blocks a bigger proportion of the light. That makes the signal clearer. That makes the data more precise. The DREAMS team took advantage of this. They observed TRAPPIST-1e during 4 separate transits. Each observation took hours. Each one was planned down to the minute, and each one generated enormous amounts of raw data that then had to be analyzed, processed, and interpreted. When they finally looked at what those observations showed, they started by asking a series of elimination questions. Because you can't just say an atmosphere exists. You have to rule out what it isn't first. Could it be a primordial atmosphere? These are atmospheres made of light gases like hydrogen and helium, the same gases that dominated the early solar system. Planets are born with these atmospheres, or at least they try to hold onto them, but small planets lose them easily. The gravity isn't strong enough to hold on to such light material, especially when a star is bombarding them with radiation and stellar wind. A primordial atmosphere would have an unmistakable signature in the light spectrum, certain absorption patterns you can't miss. When the DREAMS team looked at their data, that signature wasn't there, so TRAPPIST-1e does not have a primordial atmosphere. That's actually good news, because a primordial atmosphere of hydrogen and helium wouldn't support life as we know it. It's too different from what Earth has. Could it be a Venusian atmosphere? Venus has a secondary atmosphere, an atmosphere that built up over time from the planet itself, but it's absolutely brutal. It's 92 times denser than Earth's atmosphere and made almost entirely of carbon dioxide. The pressure at the surface would crush you instantly. The temperature would melt lead. If TRAPPIST-1e had an atmosphere like that, the data would show massive amounts of carbon dioxide absorption, huge dips in the light spectrum at the wavelengths where CO2 absorbs strongly. The data didn't show that either. The carbon dioxide signature, if it's there, is not dominant. TRAPPIST-1e does not have a thick, Venusian hellscape of an atmosphere. What about a Martian atmosphere? Mars has a secondary atmosphere that's incredibly thin. It's almost entirely carbon dioxide, but there's so little of it that the pressure is less than 1% of Earth's. If TRAPPIST-1e had a Martian-type atmosphere, the absorption signatures would be very faint. There wouldn't be much gas to absorb light, so you'd see barely any deviation from the baseline. The observations from Webb showed stronger signatures than that, more gas than a thin Martian atmosphere would produce. So TRAPPIST-1e is not a Mars-like world with a vestigial atmosphere barely clinging to survival, which means something else is going on. What the data actually pointed toward was the possibility of an Earth-like atmosphere, an atmosphere dominated by heavy gases like nitrogen, with greenhouse gases mixed in like water vapor, carbon dioxide, and potentially methane. An atmosphere with a surface pressure around 1 bar, the same as Earth. That's the working hypothesis that emerged from the initial analysis. Now, I need to be really careful here, because this is where a lot of the popular media coverage went into overdrive. Earth-like atmosphere found, the headlines screamed. And technically that's accurate, but it's also incomplete, because the data doesn't prove an Earth-like atmosphere exists. What it does is suggest that scenario is consistent with the observations. Let me explain the difference. Science works through elimination and probability. You gather data, you ask what explanations fit that data. Then you ask which explanation is most likely given what you know about physics, about planets, about how the universe works. An Earth-like atmosphere fits the James Webb observations. It explains the detected absorption patterns. But so does another possibility. There's what you might call a cold Earth scenario. An Earth-like atmosphere, but a planet that's actually quite cold. The star is so dim that even being in the habitable zone might mean TRAPPIST-1e is receiving less energy than we initially calculated. Maybe it's colder than Earth. Maybe it's more like early Earth, or like parts of Earth's polar regions. The atmosphere could still be Earth-like, with nitrogen and CO2 and water, but the surface could be significantly colder. Then there's the methane scenario. Some models suggest that high levels of atmospheric methane could produce what's called a reverse greenhouse effect. Because TRAPPIST-1 is so cool compared to our sun, it emits most of its energy in the near-infrared. Methane absorbs near-infrared radiation very efficiently, but when it absorbs and re-emits that energy, it re-emits some of it back into space. This creates cooling rather than warming. A reverse greenhouse effect. If that's what's happening, then you might have a cold, tidally locked planet. The day side could be warm enough for liquid water, but only in a narrow band. The rest of the planet would be frigid. You'd have what scientists call terminator habitability, a habitable zone that's literally the terminator line between day and night, a band of perpetual twilight where conditions could support life. It sounds alien because it is. The data doesn't tell us which scenario is correct. Not yet. That's the thing about preliminary observations. They open doors, they raise possibilities, but they don't close the case. That's why the DREAMS team has 15 more transit observations planned before the end of 2025, 15 more chances to gather data, 15 more opportunities to narrow down what's actually happening on that distant world. But here's what we do know with reasonable confidence. TRAPPIST-1e has an atmosphere of some kind, not a primordial one, not a Venusian hellscape, something more substantial than Mars, something that could potentially support liquid water and the chemistry of life. And that alone is revolutionary. You see, we've been searching for exoplanets for decades. We've found thousands of them, but detecting an atmosphere on an Earth-sized planet around a distant star, that's brand new. That's never been done before at this level of precision and clarity. Every exoplanet atmosphere we've detected until now has been on massive planets, Jupiter-sized gas giants, where the atmosphere is so huge and dense that it's relatively easy to see. Detecting an atmosphere on a small rocky world, that's a whole different challenge. The fact that James Webb pulled it off says something profound about what we can now achieve. It means we're entering a new era of exoplanet science. It means we can start asking real questions about which worlds might harbor life and which ones probably won't. It means we can begin the process of genuine reconnaissance of potentially habitable worlds. But before we get too excited, before we start imagining colonies on TRAPPIST-1e or writing science fiction about what kind of aliens might be living there. We need to confront the fundamental problem. The problem that, honestly, keeps planetary scientists awake at night. How does any of this survive? A planet can have an atmosphere. It can have liquid water. It can have all the chemical ingredients for life. But if that atmosphere is being continuously stripped away by a violent star, if it's being eroded faster than it can be replenished, then it doesn't matter. All those ingredients will eventually vanish. The planet will become a dead rock. And TRAPPIST-1 is a stellar problem. You've got to understand what red dwarfs do. They're not gentle, stable stars like our sun. They're temperamental. They're violent. They throw tantrums that would make even the most aggressive weather on Earth look mild. Solar flares happen on our sun too. We get them, but they're relatively rare and relatively contained. The worst solar storms on Earth occur maybe once a century. They cause geomagnetic disturbances. They can knock out power grids and satellites, but they pass. They don't happen every single day. TRAPPIST-1 is different. Observations suggest it emits stellar flares that rival the most powerful outbursts from our sun, roughly once every 2 days on average. Some estimates put the rate even higher. Every single day on TRAPPIST-1 potentially brings stellar violence, equivalent to a once-a-century storm on Earth. When these flares happen, they release enormous amounts of energy in multiple forms. There's electromagnetic radiation across the spectrum. There's particle radiation. There are charged particles that get accelerated to tremendous speeds. All of this hits TRAPPIST-1e directly. The planet has nowhere to hide. It's not shielded by a protective magnetic field created by a massive gas giant between it and the star, like Earth is sometimes protected by Jupiter. TRAPPIST-1 is just hanging there, exposed. The energy from these flares is sufficient to cause what's called atmospheric erosion. The particles and radiation can knock molecules loose from the atmosphere. They can strip away gases. Over time, over millions and billions of years, this process can completely remove an atmosphere. Now, how much atmosphere are we talking about that needs to survive? That's where it gets interesting. An atmosphere doesn't need to be a thick shroud. Earth's atmosphere is actually pretty thin relative to the planet's size. If you shrunk Earth down to the size of a basketball, the atmosphere would be thinner than a coat of paint. Thin, but incredibly important. TRAPPIST-1e, if it has an atmosphere similar to Earth's, would be similarly thin, but it would still be vulnerable to stripping. The question becomes, how much gas is being lost to stellar flares versus how much is being replenished from the planet's interior? Because here's the thing, atmospheres don't just exist statically, they're dynamic. On Earth, volcanoes constantly release new gases. The planet's interior is continuously pushing material outward. That outgassing is what built Earth's atmosphere in the first place over billions of years. It's what keeps it replenished. If you remove all the volcanoes, if you stop the outgassing, eventually the atmosphere would vanish through various loss mechanisms. The same process has to be happening on TRAPPIST-1e. If its atmosphere is real, the planet has to be actively replenishing its atmosphere through volcanic activity. It has to be releasing gases from its interior faster than they're being stripped away by stellar flares. That requires the planet to be geologically active. It requires internal heat. It requires a mechanism that keeps the planet warm enough to maintain volcanism despite being tidally locked to its star, despite facing eternal daylight on one side and eternal darkness on the other. And that's where we get into the really fascinating physics. Planets don't just cool passively. If a planet was initially hot from its formation, sure, it'll cool over time through radiating heat into space. But certain planets have internal heat sources that keep them warm. On Earth, that's mainly radioactive decay in the core. Uranium, thorium, potassium. These elements decay slowly, releasing heat continuously. That's why Earth's interior is still hot, billions of years after formation. On TRAPPIST-1e, you'd have similar radioactive heating. But there's potentially another mechanism too, one that's much more interesting. Tidal heating. When an object orbits another object, gravity doesn't pull uniformly on all parts. The side closer to the gravitational source feels stronger pull. The far side feels weaker pull. This difference, this gradient in gravitational force, creates stress. It stretches and squeezes the orbiting object. For a planet that's tidally locked, that means the side facing the star experiences stronger force than the backside. But here's the key. If the orbit isn't perfectly circular, if it's slightly elliptical, then the strength of this force varies as the planet orbits. Sometimes it's closer, sometimes farther. Sometimes the squeezing is more intense, sometimes less. This continuous stretching and releasing, this flexing of the planet's solid body, creates friction. Friction generates heat. It's the same mechanism that makes Jupiter's moon, Io, the most volcanically active body in our solar system. Io has an elliptical orbit around Jupiter. The gravity from Jupiter stretches it, then releases it, then stretches it again, constantly. The tidal heating from this process generates enough energy to keep Io's interior molten. The surface is covered with active volcanoes. It's a hellscape of geological violence. TRAPPIST-1e experiences tidal heating too. The calculations suggest it receives roughly 24 times as much tidal heating flux as Earth receives from its own sources. That's 24 times more heat being pumped into the planet's interior through orbital mechanics. That means TRAPPIST-1e should have a molten interior. That means volcanoes. That means outgassing. That means a mechanism to replenish the atmosphere. The math actually starts to work. The physics starts to make sense. You can have a tidally locked planet with a secondary atmosphere that survives despite constant stellar bombardment because the atmosphere is being continuously refreshed from volcanic outgassing. But there's still a complication. Red dwarfs don't just emit steady radiation. They emit X-rays and ultraviolet radiation at much higher levels than our sun does. This radiation is particularly effective at stripping atmospheres because it ionizes particles. It creates a process called photoevaporation. Essentially, the upper atmosphere gets ionized, and then the planet's solar wind can carry it away. Models suggest that early in the life of a red dwarf system, when the star is young and more active, this photoevaporation can be brutal. A young red dwarf can strip atmospheres much more efficiently than an older one. The question is whether TRAPPIST-1e managed to build up a secondary atmosphere before the star calmed down, or whether it lost whatever atmosphere it had and is only recently rebuilding one. The star is 7.6 billion years old. For the first several billion years of that, it was probably much more active. The atmosphere erosion rate was probably much higher. If TRAPPIST-1e formed with a primordial atmosphere or quickly generated a secondary one, it might have been stripped away during that early violent period. But TRAPPIST-1 is now in its main sequence phase. It's calmer, still active, still violent by our standards, but calmer than it was, less effective at atmospheric stripping, more conducive to atmospheric survival. So theoretically, over the past few billion years, TRAPPIST-1e could have rebuilt an atmosphere, volcanoes releasing gas, the gas accumulating, a new atmosphere forming, an atmosphere that's now stable enough to persist. That's the working hypothesis. That's how scientists make sense of what James Webb found. The data suggesting an atmosphere exists makes sense within this framework. It's not contradicted by physics. It's not impossible. It's actually plausible given what we know about how planets work. But plausible and proven are different things. The data is consistent with an atmosphere. Consistent doesn't mean certain, which is why the next 15 observations matter so much. Because with more data, with multiple transits analyzed in detail, the team can start pinning down specifics. They can determine whether certain gases are present or absent. They can measure absorption signatures with even greater precision. They can start answering the question that everyone wants answered. Is this atmosphere actually habitable? Could life exist there? And that answer is more complicated than you might think. The concept of habitability has gotten more flexible over the past 20 years. We used to think of habitable zones very narrowly. A planet had to be basically like Earth, similar size, similar distance from its star, similar atmosphere, similar everything. Anything that deviated too much from that template was written off as uninhabitable. But that's a profoundly limited way of thinking. We've discovered life on Earth that thrives in environments we thought were completely sterile. Life in boiling hot springs at temperatures that would cook eggs in seconds. Life in sub-zero Antarctic ice, frozen solid. Life miles beneath the ocean surface where no sunlight reaches, thriving on chemical energy from hydrothermal vents. Life in caves with zero sunlight for millions of years. Life is far more adaptable than we gave it credit for. This doesn't mean anything goes. There are constraints. Chemistry still matters. Physics still matters. But the range of possible habitable conditions is much broader than we used to think. With that framework in mind, let's talk about what could actually live on TRAPPIST-1e, assuming the atmosphere exists and the planet is generally stable. First, let's consider the scenario that everyone gets excited about. The best-case scenario. TRAPPIST-1e has an Earth-like atmosphere, nitrogen-dominated with carbon dioxide and water vapor creating a greenhouse effect, a surface pressure around 1 bar, and importantly, the atmospheric circulation is efficient enough to transport heat from the day side to the night side, creating a habitable climate across the entire planet. If this is true, then you could have a genuine global ocean, water covering the entire surface, despite the planet being tidally locked. The day side would be warm, maybe tropical, the night side would be cold, maybe icy, but the ocean would circulate, wind patterns would carry heat, the whole system would be dynamic and potentially stable. And if you've got liquid water, an atmosphere, and chemical energy sources in the planet's interior through volcanism, then you've got the basic ingredients for life. You could have something fundamentally similar to Earth, maybe not identical. The creatures would be different, the ecosystems would be different, the evolutionary paths would diverge completely, but the underlying principle would be the same: chemistry enabling biology. That's the headline scenario. That's what gets people excited. But there are other possibilities, and frankly, some of them are arguably more interesting from a scientific standpoint. Consider a different configuration. TRAPPIST-1e has an Earth-like atmosphere, but it's colder than we initially calculated. Maybe the star is putting out less energy than we thought, Or maybe there are clouds or reflective surface features that reduce the energy absorption. The day side is still warm enough for liquid water, but the global ocean scenario doesn't work. Instead, you have oceans on the day side and ice on the night side. That's still habitable. Oceans can support enormous amounts of life. They could become incubators for chemistry, for bacteria, for everything you need to get biology started. And with active volcanism, with hot vents on the ocean floor, you'd have a chemical energy gradient that life could exploit. Life doesn't actually need sunlight to exist. It needs an energy source. Sunlight is just one possibility. Or consider this scenario. TRAPPIST-1e has an atmosphere with elevated levels of methane. This creates a reverse greenhouse effect, making the planet colder than a nitrogen-dominated atmosphere would. The day side experiences significant solar heating, but it's not distributed globally. Instead, you get what scientists call the terminator zone habitability scenario. The terminator is the boundary between day and night. On a tidally locked planet, that's a specific geographic region, a band that circles the planet where day transitions to night. In the terminator zone, you'd have eternal twilight. Temperatures would be moderate. You'd have sunlight, but not intense, beating down on you sunlight. You'd have shelter from the heat of the day side and the cold of the night side. Models suggest that this zone could actually be quite wide. Wind patterns, air circulation, temperature gradients, all of these could create a climate in the terminator zone that's actually pretty habitable. Some models suggest organisms could thrive there. You could have a biosphere that hugs the terminator, a ribbon of life that circles the planet. It sounds alien because it would be. Nothing like that exists on Earth, but it's not implausible. It's not contradicting any fundamental physics or chemistry. And if you wanted to find truly exotic life that evolved under conditions genuinely different from Earth, that's where you'd look. But wait, there's another scenario that might actually be the most interesting of all. What if TRAPPIST-1e's surface is covered in ice? What if the day side is frozen, the night side is frozen, the entire globe is locked under a sheet of ice? You might think that rules out life. You might think an ice-covered world is sterile. But actually, some of the most interesting locations in our solar system for potential life are ice-covered worlds. Europa, the moon of Jupiter, is covered in ice. Beneath that ice is an ocean. We know this because we've observed the ice cracking and refreezing, evidence of something actively churning beneath the surface. That something is almost certainly liquid water, kept in a liquid state by tidal heating from Jupiter's gravity. Enceladus, a moon of Saturn, is similar, ice-covered with a subsurface ocean and active geysers that shoot water plumes thousands of kilometers into space. We've actually sampled those geysers with spacecraft. We found organic chemistry in them. This is a world that could harbor life beneath its icy shell. TRAPPIST-1e could be like that. A frozen world on the outside, but with active volcanism keeping the interior warm. An ocean beneath the ice. Hydrothermal vents on the ocean floor releasing chemical energy. All the ingredients for life, hidden beneath a protective shell of ice. The advantage of this scenario is that ice acts as a shield. It protects the ocean from direct bombardment by stellar radiation and particles. It shields from UV radiation. Anything living in that subsurface ocean would be protected. The harsh stellar environment wouldn't reach it. This might actually be more likely than a global ocean exposed to the open sky. Because if TRAPPIST-1e does have elevated methane levels, if it does experience atmospheric cooling, if the star's energy output really is lower than we initially calculated, then the planet would naturally be cold. Ice would naturally form on the surface. You'd end up with an icy world, and an icy world with a subsurface ocean. That's not just habitable. That's potentially one of the most protective environments you could find for life on any planet around a red dwarf. Because beneath that ice, life would be shielded from the stellar violence. The ice would filter out the radiation. The temperature would remain relatively stable. The chemistry would continue. This is why scientists are so interested in worlds like Europa and Enceladus, not because they're definite harbors of life, but because they represent a genuinely viable scenario where life could exist despite an apparently hostile surface environment. They're reminders that habitability is more nuanced than it appears. Now, all of these scenarios, global ocean, terminator zone, subsurface ice world, they all depend on one thing. They all depend on TRAPPIST-1e actually having a stable secondary atmosphere. Because without an atmosphere, or with an atmosphere that's rapidly disappearing, you're looking at a dead rock. All the potential vanishes. The planet becomes just another sterile world orbiting a star. So the question becomes, how stable is the atmosphere really? How well can it survive the stellar onslaught? Here's where the data from James Webb becomes even more crucial, because over the next several months, As the DREAMS team observes more transits, they're going to look for specific gases. They're going to search for carbon dioxide signatures. If carbon dioxide is present, it suggests a thicker, more stable atmosphere. CO2 is a heavy molecule. It stays put. Planets don't easily lose CO2 from their atmospheres unless something dramatic happens. If they find abundant water vapor, that's another story. Water vapor is more vulnerable to escape, especially when exposed to stellar UV radiation. High water vapor levels could indicate active outgassing from the planet's interior. It could mean the atmosphere is young, recently released from the planet. If they detect methane, that opens up the reverse greenhouse effect scenario. That fundamentally changes the climate calculations. That could explain why the planet might be colder than we expect. And if they don't find any of these gases, if the atmosphere turns out to be something entirely unexpected, well, then we're back to the drawing board. Then we have to revise our models. Then we have to figure out what's going on. The uncertainty is actually part of what makes this so compelling. We're not watching the confirmation of a foregone conclusion. We're watching genuine scientific discovery unfold in real time. The data hasn't been fully collected. The interpretations haven't been finalized. This is frontier science. But here's what strikes me about all of this. Regardless of which scenario turns out to be correct, regardless of whether TRAPPIST-1e has a global ocean, or terminator habitability, or a subsurface ice ocean, there's a deeper principle at work. Life finds a way, life adapts, life discovers pathways through environments that seem impossible from an outside perspective. I don't say that carelessly. I don't mean it as some romantic notion. I mean it as a statement grounded in what we actually know about the chemistry and physics of life. Given energy, given chemistry, given time, life emerges. That's not speculation or philosophy. That's what the geological and biological record shows us. On Earth, life appeared remarkably quickly after conditions allowed it. Some estimates suggest life arose within a few 100 million years of the planet becoming habitable. That's fast on a cosmic scale. That's evidence that the transition from chemistry to biology isn't incredibly difficult. The barrier isn't impossibly high. Now, we don't know that life would emerge on TRAPPIST-1e specifically. We don't know that it started there. We have no evidence one way or the other. But we do know that if the conditions are right, if the chemistry works out, if the energy sources exist, then life becomes statistically probable rather than miraculous. And TRAPPIST-1e has the conditions, it has the chemistry, it has the energy sources, tidal heating, volcanic outgassing, an atmosphere, potentially liquid water. Everything is there. Could it be lifeless anyway? Absolutely. Maybe life is rarer than we think. Maybe there are conditions we don't understand yet that are necessary. Maybe TRAPPIST-1e is a world that looks habitable but remains eternally sterile for reasons we haven't figured out. But statistically, given what we know, the probability tips the other direction. If this world exists, if it has an atmosphere and liquid water and chemistry, then life is more likely than not. That's a profound shift in how we think about the galaxy. For decades, we've assumed that habitable planets are rare. We've built our entire search strategy around the assumption of rarity. But if habitable conditions are actually common, if most planets in the habitable zones of their stars actually develop life, then the galaxy is full of biology, full of activity, full of life. And we might actually be able to search for it soon. Because here's the thing that most people don't realize. James Webb can do more than just detect atmospheres. It can, in principle, detect the chemical signatures of biological activity. If a planet has oxygen in its atmosphere at levels that shouldn't be there given normal chemistry, that's a biosignature. Life produces oxygen as a waste product. Oxygen is a highly reactive element. It should be consumed by other reactions on a geologically active planet. High oxygen levels might indicate biological production. Similarly, methane combined with other gases in certain ratios could indicate life, because there are chemical processes that produce methane, but there are also biological processes. Microbes in wetlands produce methane. If you saw methane at levels that didn't quite fit normal chemistry, if you saw it alongside other compounds that suggested biological activity, that would be a biosignature. Webb isn't currently optimized to search for biosignatures. That's beyond its capabilities for now. But we're building telescopes that will be the Habitable Worlds Observatory. The flagship telescope planned for launch in 2041 is specifically designed to search for atmospheres on potentially habitable planets and analyze them for biosignatures. That's still 16 years away, but it's coming. And when it arrives, TRAPPIST-1e will probably be one of the first targets, because we already know it has an atmosphere. We already know it's in the habitable zone. We already have preliminary evidence that something interesting is happening there. In 2041, we might get the answer. We might be able to look at TRAPPIST-1e's atmosphere and ask directly, is there life? But we can't wait until 2041. The data is coming in now. The mystery is unfolding now. And the implications are already transforming how we think about the universe. Because if TRAPPIST-1e is habitable, if it actually hosts life or could support life, then what does that tell us about the galaxy? It tells us that habitable planets aren't rare. It tells us that life-supporting conditions can exist in places we thought were too hostile. It tells us that the universe might be far more populated than we ever imagined. And it tells us something else, something that might be even more profound. We're not alone, maybe not nearby, maybe not visibly, but statistically, probably not alone. The conditions we find so extraordinary, a planet with an atmosphere, with liquid water, with energy sources, those conditions probably exist on millions of worlds throughout the galaxy. And if they exist, chemistry happens. If chemistry happens, biology probably emerges. We might be one of billions of worlds with life. Billions. Not because of anything special about us, just because those conditions are common, and life is what naturally arises when conditions allow it. That's a shift in perspective that's hard to overstate. Humanity has spent most of history thinking we were unique, special, uniquely blessed or cursed with consciousness. Science has been gradually walking that back. We're not the center of the universe. Our planet isn't unique. Our star isn't special. And now, our situation, a habitable world with life, probably isn't unique either. We're probably just one among billions. TRAPPIST-1e is evidence of that. A distant planet around a dim star, unremarkable by most measures, probably harboring conditions not so different from Earth. And if that's true, then when we look through telescopes, when we scan the nearby stars, we're probably looking at worlds that are genuinely similar to ours, full of chemistry, potentially full of life. That's not speculation. That's what the data suggests. That's what the physics allows. And it all started with a telescope pointing toward a distant star and asking, what's in that atmosphere? But before we get too caught up in the philosophical implications, we need to address the elephant in the room, the thing that should make you skeptical, the thing that makes a lot of scientists skeptical too. The data isn't final. The analysis is preliminary. What we're looking at are suggestions, hints, indicators that point toward an atmosphere, but we don't have proof yet. We don't have certainty. And in science, there's a world of difference between the data is consistent with an atmosphere, and we've definitely found an atmosphere. That gap is where mistakes happen. That gap is where exciting findings get overtaken by mundane reality. We've been down this road before. We've found signals that seemed profound and turned out to be noise or artifacts or misinterpretation. So let me walk you through what the actual uncertainties are, what the limitations are, because understanding the limits of what we know is just as important as understanding what we think we know. First, there's the inherent ambiguity in transmission spectroscopy. When you measure light that's passed through an atmosphere, you're measuring the combined effect of all the gas in the atmosphere. You're not getting a detailed composition, you're getting a fingerprint, and fingerprints can be tricky to interpret. Different atmospheric compositions can produce similar absorption patterns. A thin atmosphere of one type of gas might absorb light similarly to a thick atmosphere of a different gas. You can't always distinguish between them with the wavelength data alone. This is especially true when you're looking at the near-infrared region where Webb observes. The DREAMS team has addressed this partially by having multiple observations. With 4 transits, you get more data points. You can start to rule out certain scenarios and narrow down others. But 4 observations is still a relatively small sample. More observations would increase confidence. 15 more observations, which they have planned, would dramatically increase confidence. Second, there's the issue of clouds. Clouds completely change how light interacts with an atmosphere. A cloudy Earth looks very different to a distant observer than a clear Earth does. The clouds reflect light. They absorb light. They alter the observed spectrum significantly. We don't know if TRAPPIST-1e has clouds. Models suggest it might. A tidally locked planet with an ocean could develop atmospheric circulation patterns that create clouds. But models aren't reality. Reality is messier, and if there are clouds, they could be affecting the spectroscopic data in ways that aren't fully accounted for yet. Clouds on a tidally locked world would be particularly interesting because they'd accumulate in certain regions. The atmosphere would circulate from the hot day side to the cold night side. As the air rises on the day side and moves toward the night side, it would cool. As it cools, moisture would condense. You'd form clouds. Those clouds would accumulate over the night side, creating a permanent cloud cover in certain regions. This would affect how you interpret the transmission spectroscopy. It would create absorption patterns that might be misinterpreted as atmospheric gases when they're actually just cloud coverage. Third, there's the possibility of systematic errors. When you're collecting data from space from an instrument that's millions of kilometers away, there are countless things that can go wrong. There's instrumental noise. There's thermal effects that can subtly shift the data. There are calibration issues, data processing choices. Different ways of analyzing the same raw observations can produce different results. The DREAMS team is aware of these issues. They're careful, but careful and perfect are different things. It's entirely possible that further analysis will reveal subtle biases in the data processing that would shift the conclusions. It's possible that new observations will be inconsistent with the preliminary interpretations. This happens in science. It's not a failure. It's how the process works. You make preliminary observations. You propose interpretations. You gather more data. You refine refine or revise your interpretations based on new evidence. Fourth, there's the question of what counts as habitable. Even if TRAPPIST-1e has an atmosphere, even if the atmosphere is stable and Earth-like, that doesn't automatically mean life lives there. It means conditions could support life. It means the chemistry is compatible with biology. But that's different from life actually being present. Earth is habitable. It teems with life. But Earth didn't always have life. For the first 500 million years or so after formation, Earth was sterile. The chemistry was right. The conditions were appropriate. But biology hadn't emerged yet, or it had emerged and then gotten wiped out by some catastrophe. The point is, habitable doesn't mean inhabited. Similarly, TRAPPIST-1e could be perfectly habitable and completely sterile. Life might not have emerged. Life might have emerged and then been destroyed. Life might be there right now. Without directly observing it, we can't know. This is why the search for biosignatures is so important. Why the Habitable Worlds Observatory matters. Because eventually we want to move beyond just detecting atmospheres. We want to ask if those atmospheres contain chemical signatures of life. That's a harder question, but it's answerable in principle. Fifth, there's a meta-level uncertainty. We're studying a planet we can't directly observe. We can't see it. We can only detect its effects on starlight. We're inferring its properties from gravitational effects and spectroscopic signatures. This is remarkably powerful, but it's also limited. There are parameters we simply can't measure directly. The exact composition of the atmosphere is one of those parameters. We can get hints from transmission spectroscopy, but we're not going to get a precise readout of every gas present. We're going to get a general picture. That picture will have gaps. Those gaps are where possibilities live. Those gaps are where you can construct multiple different scenarios that all fit the data. Given all these uncertainties, given all these limitations, why should you take this discovery seriously at all? Why is anyone excited about it? The answer is that despite the uncertainties, despite the limitations, the fundamental conclusion remains robust. TRAPPIST-1e almost certainly has some kind of atmosphere. Not a primordial hydrogen-helium atmosphere, not a vacuum, an actual genuine atmosphere composed of heavier elements. That conclusion is hard to escape given the spectroscopic data. That conclusion survives most of the alternative explanations. And if you accept that TRAPPIST-1e has an atmosphere, then you're forced to accept implications that are genuinely profound. Because having and maintaining an atmosphere on a planet being bombarded by stellar radiation from a red dwarf is hard, really hard. The fact that TRAPPIST-1e apparently managed it means we've underestimated something. Either we've underestimated how resilient atmospheres can be, or we've underestimated how effective planetary outgassing can be at replenishing atmospheres, or we've underestimated how much the TRAPPIST-1 system has evolved toward greater stability over its 7.6 billion-year history. Any of those possibilities changes how we think about habitability in red dwarf systems. Red dwarfs are by far the most common type of star. Roughly 80% of stars in our galaxy are red dwarfs. If red dwarf planets can maintain stable atmospheres, if they can develop habitable conditions despite being in violent stellar environments, then the implications are staggering. The number of potentially habitable planets around red dwarfs in the galaxy is probably in the billions, maybe tens of billions. It's hard to estimate precisely, but the numbers are enormous. And if most of those have developed atmospheres and habitable conditions, then the galaxy is probably teeming with life. That changes everything. It changes how we prioritize the search for extraterrestrial life. It changes what telescopes we build. It changes what questions we ask. It changes how we think about our place in the universe. All of that flows from one fundamental conclusion. TRAPPIST-1e has an atmosphere, a real atmosphere, a secondary atmosphere built up over time through planetary outgassing, an atmosphere that's survived billions of years of stellar violence. If that's true, and the data suggests it is, then we need to take seriously the possibility that life exists on distant worlds. We need to take seriously the possibility that we'll find it within our lifetime through telescopic observation. We need to take seriously the possibility that the universe is not the sterile, mostly empty place we've often imagined. We need to take it seriously because the alternative, dismissing this discovery as preliminary or uncertain, might be the biggest mistake we could make. Because if we ignore the evidence in front of us, if we assume that TRAPPIST-1e is unusual rather than common, if we continue to assume that habitable planets are rare, then we'll continue to search ineffectively. We'll continue to miss opportunities. We'll continue to look in the wrong places. But if we take the evidence seriously, if we assume that TRAPPIST-1e is probably typical of Earth-like planets around red dwarfs, if we assume that atmospheres and habitability are common, then our entire approach changes. We'll start looking differently. We'll ask different questions. We'll find things we would have otherwise missed. That's the real power of this discovery, not the specific finding about TRAPPIST-1e. That's important, but it's local. The real power is the paradigm shift, the realization that habitability might be ubiquitous rather than rare, that life-supporting conditions probably pervade the galaxy, that we're probably just one world among billions with biology. Now, the scientists involved with this research know all of this. They understand the implications, And that's why they're continuing to observe. That's why 15 more transit observations are planned. That's why the DREAMS team is pushing James Webb to its limits, gathering as much data as possible about TRAPPIST-1e, because they want to know, because the answer matters, because if TRAPPIST-1e really is a habitable world, if it really does have a stable atmosphere and potentially life, then humanity is entering a new era, an era where we can actually search for life on distant worlds, an era where we might actually find something. But that era hasn't arrived yet. The data is still being collected, the interpretations are still being refined, the conclusions are still being challenged and tested and examined from every angle. What we have right now is a strong signal, a compelling hint, evidence that points towards something extraordinary. But we need more. We need the additional observations. We need the refined analysis. We need time for the scientific process to do its work. And in the meantime, what should you think? Should you accept that TRAPPIST-1e is habitable? Should you assume life probably exists there? Should you be skeptical and assume the discovery will be overturned? Honestly, the answer is somewhere in the middle. The evidence is solid enough that you should take it seriously. The atmosphere detection is likely real. The habitability is plausible. Life is possible, but it's not certain. And certainty matters, especially in science. What you should do is stay curious, stay interested, follow the updates as they come. Watch for the results of the additional observations. Think about what the implications would be if TRAPPIST-1e really is habitable. Think about what it would mean for the galaxy and for humanity's place in it, because over the next few months, the data is going to keep coming in, the team is going to keep observing, and our understanding of TRAPPIST-1e is going to keep evolving. By the end of 2025, we might have much better clarity on whether this world has a permanent atmosphere or whether the initial signal was something else. And depending on what that data shows, we might be standing at the threshold of a genuine revolution in how we think about life in the cosmos. We might be on the verge of confirming that habitable worlds aren't rare, that they're actually common, that the galaxy is full of them. Or we might discover that TRAPPIST-1e is a false alarm, a planet that looked habitable but turned out to be something else. A reminder that the universe is often more subtle and more complex than our initial interpretations suggest. Either way, we're learning. Either way, the search continues. Either way, we're getting closer to understanding our place in the universe. And that's worth paying attention to. Now let's talk about something that gets less attention but might be equally important. Let's talk about what happens next. Not years from now, not with future telescopes, right now. What's actually happening in the scientific community as this data comes in? Because here's something that doesn't always get covered in popular science writing. Scientists don't just accept data and move forward. They challenge it. They poke holes in it. They try to break it. They look for alternative explanations. They argue with each other about what the data means. This is a feature, not a bug. This is how science self-corrects. This is how we avoid building understanding on faulty foundations. In the case of TRAPPIST-1e, there are astronomers and planetary scientists who are skeptical of the atmosphere detection. Not because they're cynical or dismissive, but because they understand the limitations of the data. They understand that preliminary interpretations are often wrong. They've seen promising discoveries get overturned before. Some of them are asking hard questions. Is the signal real, or could it be an artifact of data processing? Could clouds alone explain the observed absorption without invoking a secondary atmosphere? Could the planet be tidally heated enough to drive atmospheric escape rather than atmospheric building? Could the initial analysis have missed something? These aren't attacks on the DREAMS team. The DREAMS team expects these questions. They want them. Because if someone can poke a hole in their analysis, they want to know about it before they publish major conclusions. This is where the peer review process comes in. The team's findings will eventually be submitted to scientific journals. Other researchers will review the work, they'll check the methodology, they'll verify the calculations, they'll ask whether the conclusions follow logically from the data. If the paper survives that process, if it passes scrutiny from independent experts, then it gains credibility. But peer review isn't instant. These things take months, sometimes years. And even after peer review, there's still skepticism, there's still debate, there's still the possibility that subsequent research will show that earlier conclusions needed revision. This is why the 15 additional observations matter so much. Because with more data, with more transits analyzed, with independent confirmation of the signal from multiple observations, the chances of a systematic error or misinterpretation go down dramatically. It becomes harder to argue that the signal is artificial when you've seen it consistently across dozens of independent observations. So what's actually happening right now, this very moment, is that the DREAMS team is collecting data. They're analyzing it carefully. They're writing papers that will soon enter the peer review process. They're preparing presentations for conferences where they'll present their findings to other scientists. They're bracing themselves for criticism and questions. and they're continuing to observe, gathering more data, trying to pin down exactly what's on TRAPPIST-1e. Meanwhile, other teams are starting to look more closely at the TRAPPIST-1 system, because now that there's a hint of an atmosphere on TRAPPIST-1e, suddenly the whole system becomes more interesting. Maybe other planets in the system have atmospheres too. Maybe the system is more complex than we thought. Maybe there are other surprises waiting to be discovered. This is how scientific interest compounds. One discovery leads to more questions. Those questions lead to more observations. More observations lead to more discoveries. A single finding can trigger an avalanche of research activity. That's what's happening with TRAPPIST-1 right now. It's becoming a focus of the astronomical community. Researchers who weren't previously interested in the system are now pointing instruments at it. Theorists are working on models to explain what observations might reveal. Everyone is waiting to see what the data shows. And this is where something interesting happens. This is where the scientific process reveals something about human nature. When there's a mystery, when there's an open question, when there's data that doesn't fit neatly into existing frameworks, scientists get energized. They get excited. They start working harder. They start collaborating more. They start thinking bigger. This is the true engine of scientific progress. It's not funding. It's not equipment. It's not institutional support, though all of those help. It's the fundamental human drive to understand, to solve puzzles, to figure out how things work. TRAPPIST-1e has become a puzzle, and the scientific community is mobilizing to solve it. Now, let's zoom out for a moment. Let's think about what the bigger picture here is. For the first time in human history, we have the capability to detect atmospheres on distant planets. Not hypothetically, not in theory, actually, practically. We can point a telescope at a star 40 light-years away and ask, what's in the atmosphere of that planet? And we can get answers. This is revolutionary. I don't use that word lightly, but this genuinely is a revolutionary capability. It changes what's possible. It changes what questions we can ask. It changes what we can actually learn about distant worlds. For most of human history, planets were invisible. They weren't even known to exist. We knew about stars. We knew about the sun and moon. We knew about comets and supernovae. But planets around other stars, that was philosophy. That was speculation. That was outside the realm of observational science. Then, in the 1990s, we detected the first exoplanet, a Jupiter-sized gas giant around a star called 51 Pegasi. It was a momentous discovery, but what could we learn from it? We could measure its mass. We could estimate its distance from the star. We could calculate its orbital period. But about the planet itself, about its physical composition, its atmosphere, its potential for harboring life, we could speculate. We couldn't really know. Over the next couple of decades, we got better at detecting planets. We found thousands of them, but we were still mostly blind. We knew they were there, but we didn't know much about what they were actually like. Then James Webb launched, and suddenly the game changed. Suddenly we could ask questions about planetary atmospheres. We could try to detect what's in them. We could start moving from detection to characterization, from knowing planets exist to understanding what those planets are. TRAPPIST-1e is one of the first targets of this new capability. It's one of the first times we've seriously tried to read the atmospheric composition of an Earth-sized planet around a distant star. And we found a signal. We found evidence of an atmosphere. The implications are enormous. Because if we can do this for TRAPPIST-1e, we can probably do it for other planets too. We can build up a catalog of planetary atmospheres. We can start asking which planets might be habitable. We can start narrowing down where to look for life. Over the next decade or two, as telescopes improve and techniques are refined, we'll probably detect atmospheres on dozens, maybe hundreds of exoplanets. We'll start to build a picture of what planets are actually like. We'll see patterns. We'll see which types of planets tend to have atmospheres and which lose them. We'll see which atmospheric compositions suggest habitable conditions. And eventually, probably within your lifetime, we'll point a telescope at a planet and see spectroscopic evidence of life. We'll see oxygen or methane or some other chemical signature that we know life produces. And we'll be able to say, with confidence based on observational evidence, that there's biology on that world. That's not in the distant future. That's something the Habitable Worlds Observatory is designed to do. That's something that might happen in the next 15 to 20 years. TRAPPIST-1e is not necessarily where life will be first detected. It might be, but there are other candidates. There are other planets around nearby stars that might be easier to study. But TRAPPIST-1e is definitely one of the most interesting. It's definitely one of the most promising. And it's definitely one of the worlds we'll be studying most intensively as this new era of exoplanet characterization unfolds. So when you look at news about TRAPPIST-1e, when you see headlines about an atmosphere detection, understand what you're really looking at. You're looking at the opening chapter of a new book, a book about understanding distant worlds, a book about searching for life, a book that might fundamentally change how we see ourselves. But here's what I want to emphasize. This isn't speculative. This isn't wishful thinking. This is real observational science. This is data that James Webb actually collected. This is analysis that actual astronomers are actually doing. This is the real scientific frontier unfolding in front of us. The only speculative part is where this leads, what we learn from additional observations, what we discover when we start looking at other worlds with the same techniques, what the broader implications turn out to be. And that's where we need to talk about the other possibility. The possibility that TRAPPIST-1e, despite having an atmosphere, despite being in the habitable zone, despite having all the ingredients we think are necessary for life, is actually sterile, completely lifeless. Because here's the thing about biology, it's incredibly robust once it gets started. But getting started is actually kind of mysterious. We don't fully understand it. We have theories, we have experiments that suggest life could arise from chemical reactions under certain conditions. But we've never seen it happen. We've never watched life emerge from non-living chemistry. On Earth it happened. We know that for certain. Somehow, somewhere, chemistry became biology. But we don't know exactly how. We don't know exactly when. We don't know whether it was easy or almost impossibly rare. If it was easy, if the conditions on Earth are common, and life readily emerges whenever they occur, then TRAPPIST-1e is probably inhabited, or at least, it probably harbors life. Microbes at minimum, maybe more complex organisms, maybe not multicellular life, but definitely biology. But if it was rare, if Earth is actually unusual, if the specific conditions for life to emerge only occur on 1 in a million planets, then TRAPPIST-1e could be habitable but sterile. It could have everything necessary for life, except for life itself. The chemistry could be right, the energy sources could be available, but the spark of biology never ignited. And without that spark, the world remains perpetually barren. Which scenario is true? We don't know yet. That's one of the biggest open questions in astrobiology, and the only way to answer it is to keep looking, to study multiple worlds, to see which ones have evidence of life and which ones don't, to gather statistics on how often life actually emerges. TRAPPIST-1e will be part of that search. It's part of the sample we're building. As we study more and more potentially habitable worlds, as we look for biosignatures in their atmospheres, we'll gradually build up a picture of how common life actually is. We'll find out whether habitability and habitedness are closely connected, or whether there are lots of dead habitable worlds out there. That's the frontier we're moving toward. That's what the next decade or two of exoplanet science is going to be about. And it all hinges on capabilities like transmission spectroscopy. It all hinges on instruments like James Webb. It all hinges on the work of teams like the DREAMS collaboration, pushing these instruments to their limits, extracting every bit of information they can from the light of distant stars. The data is coming in, the observations continue. The mystery of TRAPPIST-1e is slowly being revealed. And by the end of 2025, we should have significantly better clarity on whether this world is truly habitable, whether its atmosphere is stable and real, whether it represents what habitable worlds are actually like. What we learn could reshape how we think about the galaxy. It could open up new avenues of research. It could fundamentally change the trajectory of the search for extraterrestrial life. Or it could turn out to be a dead end, a fascinating world that doesn't quite fit the mold we expected. A reminder that the universe is full of surprises, and that our models don't always match reality. Either way, we're learning. Either way, the frontier is advancing. Either way, we're moving closer to understanding whether we're alone in the universe or whether we're just one among billions of worlds with biology. And that's what makes this moment genuinely thrilling. Let me take you somewhere specific now. Let me walk you through what a day on TRAPPIST-1e might actually be like, assuming the atmospheric scenarios we've been discussing are real, because this is where the abstract physics becomes concrete, where the numbers translate into actual conditions, where you can start to really visualize what this world might be. Imagine standing on the surface. It's always the same time of day. The star, TRAPPIST-1, never moves across the sky. It stays fixed. You're on the side of the planet that faces the star, so it's always there, always present, never setting, never rising, perpetual day. But it's not like Earth's day. The star is red, deeply red, optical red. If you looked up at the sky, the starlight would have a reddish tint to everything. It would be like standing in perpetual sunset. The colors would be muted compared to Earth. Blues would be suppressed. Reds and oranges would dominate. It would be alien, beautiful in its own way, but genuinely alien. The light level would be about 2/3 of what you get at Earth's equator. That's not darkness. That's not twilight. That's legitimate daylight. Plants, if they existed, could photosynthesize. There's enough energy, but it would be dimmer. The sun would be less bright. The shadows would be softer, and the star itself would look different. From Earth, the sun looks like a small bright disk in the sky. That's because it's far away. From TRAPPIST-1e, where the planet is so close to its star, the star would look enormous, 4 times larger in angular size than our sun looks from Earth. It would dominate the sky. It would be impossible to ignore. The temperature on the day side, assuming an Earth-like atmosphere with greenhouse warming, would probably be warm, maybe tropical, maybe subtropical. Data models suggest somewhere in the range of 30 to 60 Celsius. That's 86 to 140 degrees Fahrenheit. Hot, but not uninhabitable. Organisms on Earth survive in much hotter environments, in hot springs, in deserts, in shallow tropical waters. But here's where it gets interesting. Thanks to atmospheric circulation, thanks to winds and storms, heat is being transported from the day side toward the night side. The atmosphere acts like a conveyor belt, carrying warmth across the terminator, out onto the dark side. As you move toward the night side, as you approach the terminator, the light would start to dim, the temperature would start to drop, the conditions would transition from tropical daylight to twilight. And if you actually made it to the night side, you'd find something remarkable. It wouldn't be completely dark. There would be starlight, the light from distant stars, just like on Earth at night. But there wouldn't be sunlight from TRAPPIST-1. That star would be behind the horizon, blocked by the planet itself. The sky would be starlit and faintly illuminated by the distant light of the day side reflecting off the atmosphere and clouds. And it would be cold. How cold depends on the details of the atmospheric circulation, but probably somewhere around -10 to -50 Celsius. That's -14 to -58 Fahrenheit. Cold enough to freeze water, cold enough to create ice formations, but not so cold as to be completely lifeless. In fact, there's an interesting middle ground, the terminator zone, the boundary between day and night, where you'd have perpetual twilight, where the temperature would be moderate, where there would be some sunlight but not intense, where you might actually find the most favorable conditions for life if TRAPPIST-1e is tidally locked. Some researchers have suggested that if life does exist on TRAPPIST-1e, it might be concentrated in this terminator zone. It might form a band around the planet, a ribbon of biology that follows the twilight. It would be a unique ecosystem, shaped by the unique conditions of a tidally locked world. Imagine that, a ring of life circling the planet, creatures that evolved in perpetual twilight, plants that adapted to the red starlight, maybe microbes, maybe more complex organisms, maybe something we can't even imagine because we've never encountered anything like it on Earth. This is the power of understanding planetary conditions. It allows you to build a mental model, to imagine what a world might be like, to think about what possibilities might exist there. Now, here's something important. We're talking about all this as if TRAPPIST-1e definitely has an Earth-like atmosphere, as if the habitable scenario is confirmed. But remember what we discussed earlier. The atmosphere detection is preliminary, it's promising, but it's not confirmed. There are other possibilities. Remember the methane scenario, the reverse greenhouse effect? That would create a much colder world. The day side might still be warm enough for liquid water, but the rest of the planet would be frozen. You wouldn't have global oceans. You wouldn't have tropical conditions. You'd have ice, frozen water, maybe a liquid water ocean only on the day side, with ice everywhere else. That's a much harsher world, but actually it might be more stable, more resistant to the stellar onslaught. If the planet is cold, if the atmosphere is thin, if water is locked in ice, then there's less gas to be stripped away by solar flares, less vulnerability. Paradoxically, a colder, harsher world might be more resilient. Or consider the subsurface ocean scenario. The planet's surface is entirely frozen. Ice covers it from pole to equator. Below the ice, kilometers down, there's a liquid water ocean. In that ocean, there are hydrothermal vents, hot springs from the planet's interior, chemical energy flowing out of the vents. That's an environment that could support life. You wouldn't see it from space. You'd just see an icy world, dead, barren. But beneath the surface, you'd have a thriving biosphere, creatures adapted to deep ocean conditions, bacteria around the vents, maybe more complex life, maybe nothing at all. You wouldn't know unless you looked. This scenario has parallels on Earth. Europa, Jupiter's moon, is almost certainly covered in an icy shell with a subsurface ocean beneath. Enceladus, Saturn's moon, is similar. We've detected geysers on Enceladus, water plumes shooting into space from beneath the ice. These worlds are genuinely interesting as potential harbors for life. TRAPPIST-1e could be like that, icy on the surface but liquid and alive beneath. Or, least optimistically, the planet could be completely barren, no atmosphere at all, just rock and dust. A dead world, the stellar radiation stripping away any atmosphere that tried to form. The tidal heating insufficient to create volcanism. No chemistry, no biology, just a sterile rock orbiting an ancient star. Which one is it? We don't know yet. That's the honest answer. The data suggests something substantial is there, but what exactly? That's what we're trying to figure out. And this is where I want to make a point about how science actually works versus how it's often portrayed. In movies and popular media, scientists make discoveries and immediately know what they mean. There's a moment of revelation. Everything clicks into place. The mystery is solved. In reality, discoveries often raise more questions than they answer. You find something, you measure it, you collect data, and then you have to figure out what it means. That takes time, it takes debate, it takes additional observations, it takes refining your understanding gradually, over months or years. The TRAPPIST-1e atmosphere detection is like that. It's a discovery, it's real data, but what does it mean exactly? That's still being figured out. The team will gather more observations, other teams will conduct independent analysis. The The scientific community will debate the implications. Gradually, over time, a consensus will emerge about what TRAPPIST-1e really is. That might happen over the next few months as more observations come in, or it might take years. Science moves at its own pace. You can't rush it without risking errors. But here's what I find genuinely exciting about this moment. We're at the beginning of something. We're at the point where we're starting to answer questions that have been purely theoretical for centuries. What are distant worlds actually like? Do they have atmospheres? Could they harbor life? For the first time, we have the tools to answer these questions. Not perfectly, not completely, but genuinely, observationally. Over the next decade, this is going to explode. We're going to study more planets. We're going to refine the techniques. We're going to get better data. We're going to detect atmospheres on dozens of worlds. We're going to start narrowing down which ones might be habitable. We're going to start building a catalogue of the galaxy's potentially life-bearing worlds. And eventually, we're going to point a telescope at a planet and see chemical evidence of biology. We're going to detect oxygen in abundance where chemistry alone can't explain it. We're going to see methane signatures that suggest microbial life. We're going to have our first genuine evidence that life exists beyond Earth. TRAPPIST-1e might be that world. It might be something else, but it's definitely part of the search. And right now, in this moment, we're watching the search actually work. We're seeing the frontier advance. That's worth understanding. That's worth paying attention to. Now, I want to shift the focus for a moment. I want to talk about something that doesn't usually get covered in discussions about exoplanets. I want to talk about why this matters beyond the abstract intellectual curiosity. Because finding life on another world would fundamentally change how humanity understands itself. It would answer one of the most profound questions we can ask. Are we alone? For most of human history, the default assumption was that we were unique. We were special. We were alone in the universe. That might have been ego. It might have been based on religious or philosophical assumptions, but it was the background assumption. Science has been gradually chipping away at that assumption. Copernicus showed Earth isn't the center. Darwin showed humans evolved through the same processes as other life. Hubble showed the universe is vast beyond imagination, full of billions of galaxies. Each discovery pushed back against human exceptionalism. But the one thing we still don't know is whether life itself is unique to Earth, whether the emergence of biology is so rare that it only happened once, whether life is essentially a miracle that occurred by incredible chance on one planet. If we discover that life exists on TRAPPIST-1e, that changes everything. It means life isn't a miracle. It means biology emerges when conditions allow. It means the universe is probably full of it. That's a fundamental shift, not just scientifically, but philosophically, culturally. It changes how we see ourselves. We're not alone. We're part of a universe teeming with life. We're probably typical rather than exceptional. Some people find that depressing. They like thinking we were special. Some people find it liberating. They like the idea that biology is common. Either way, it's a profound shift, and it might happen soon, within your lifetime, within the next decade or two. It might happen through studying TRAPPIST-1e or some other world, but it's going to happen. The trajectory of progress in exoplanet science suggests that we're going to find evidence of extraterrestrial life relatively soon. When that happens, when we have real observational evidence that life exists elsewhere, it's going to be one of the biggest moments in human history. It's going to rival the scientific revolutions that came before. It's going to reshape how we think about everything. And TRAPPIST-1e might be the world that triggers it. Or if not TRAPPIST-1e specifically, then a world very much like it. A rocky planet around a red dwarf, a secondary atmosphere, habitable conditions, and life. Real, actual life on another world. That's what we're moving toward. That's the frontier we're on the edge of crossing. But let me bring this back down to Earth for a moment. Let me ground this in the actual science that's happening right now, because it's worth understanding the mechanics of what comes next. The DREAMS team has scheduled 15 more observations of TRAPPIST-1e before the end of 2025. That's roughly one observation every few weeks. Each one will collect new transmission spectroscopy data. Each one will add to the dataset. Each one will help narrow down what's actually on that planet. Now you might think, why not do all the observations at once? Why spread them out over time? The answer has to do with how orbits work. The planet transits its star in a predictable pattern, but those transits don't happen every day. They happen according to the planet's orbital mechanics. TRAPPIST-1e orbits once every 6.1 Earth days. But we can only observe transits when the orbital geometry is right, when the planet actually passes between us and the star, and when the James Webb telescope is available. So the observations are scheduled during the optimal windows. As those data come in, the team will process them. They'll run them through analysis pipelines. They'll compare them to models. They'll look for consistent signals. They'll try to identify which atmospheric gases are actually present. By the end of 2025, if all goes as planned, they should have significantly more confidence in their conclusions. They might be able to say definitively whether carbon dioxide is present or not. They might be able to determine whether the atmosphere is primarily nitrogen or methane or something else. They might be able to narrow down the surface conditions dramatically. But here's what's interesting from a broader perspective. This isn't happening in isolation. Other teams are doing their own work. Some are studying TRAPPIST-1e with different instruments. Some are studying other planets in the system. Some are building theoretical models to see if various atmospheric compositions make physical sense. This is how science works at the frontier. Multiple teams, multiple approaches, different perspectives, all of it converging toward a more complete understanding. And the results from James Webb will feed into a larger scientific effort. Because once we understand TRAPPIST-1e better, once we know more about what it's actually like, that understanding feeds into broader questions about habitability, about which planets are worth studying, about where to look for biosignatures, about which targets to prioritize for future observations. There are about 50,000 potentially habitable exoplanets thought to exist within 200 light-years of Earth. 50,000. Most of them we know almost nothing about. We don't know their atmospheric composition. We don't know their surface conditions. We don't know whether they're actually habitable or just theoretically in the habitable zone. The James Webb telescope can't observe all of them. It can't even observe a significant fraction. James Webb is in high demand. There's competition for observation time. The DREAMS team spent years building up their case for why TRAPPIST-1e deserved their guaranteed observation allocation. So what gets studied? What becomes a priority? Partly it's scientific merit. How likely is the target to yield interesting results? But partly it's also practical. How accessible is the target? How easy is it to observe? How bright is the star? How deep can you dig into the data? TRAPPIST-1e scores well on both fronts. The star is relatively dim, which makes the transit signal clearer. The planet is close enough that we can actually study it in reasonable detail. And given the preliminary evidence of an atmosphere, it's scientifically compelling. So it's getting studied. And the results are going to shape how we approach exoplanet science for the next decade. Now let me talk about something that's important but often gets overlooked in popular coverage: the engineering and logistics involved in doing this kind of science. James Webb is in an orbit called the second Lagrange point, or L2. That's a spot where the gravitational pull of the Earth and Sun balance out in a specific way, allowing an object to stay relatively stationary with respect to both bodies. L2 is about 1.5 million kilometers from Earth. That's 4 times the distance from Earth to the Moon. Operating a telescope that far away is genuinely challenging. Any observation has to be carefully planned and uploaded to the spacecraft weeks in advance. The spacecraft executes the observations automatically. The data is collected and stored. Then it's transmitted back to Earth over several days using radio signals. By the time the data arrives back on Earth, it's been traveling through space for thousands of seconds. It needs to be decoded. It needs to be corrected for various instrumental effects. It needs to be processed through multiple steps before it's ready for analysis. All of that takes time. All of that introduces possibilities for error. All of that requires skill and careful attention to detail. The DREAMS team has done this before. They've worked with exoplanet data. But this is different because they're pushing James Webb to its limits. They're trying to extract the maximum possible information from every photon that reaches the instrument. They're using techniques that have been refined over years of observation, and it's paying off. The data they're getting is unprecedented in quality. It's revealing things about TRAPPIST-1e that we couldn't have known just a few years ago. But here's what I find genuinely remarkable about all of this. The capability to do this kind of science is relatively recent. James Webb itself launched in December 2021. It took until mid-2022 for it to reach L2 and have its instruments commissioned. The current observations of TRAPPIST-1e started in 2024 and are continuing into 2025. We're talking about a capability that's less than 2 years old. In 2 years, we've gone from not being able to detect atmospheres on Earth-sized exoplanets to having preliminary evidence of an atmosphere on one specific world. That's an incredibly rapid advance. That's how fast the frontier is moving. And looking ahead, it's only going to accelerate. Better calibration of James Webb's instruments will come with experience. New techniques for analyzing transmission spectroscopy data are being developed constantly. More observations are being planned. More teams are getting access to the instrument. Within 5 years, we're probably going to have atmospheric data on dozens of planets. Within 10 years, maybe 100. Within 15 to 20 years, we might have atmospheric analysis of thousands of potentially habitable worlds. From that data set, patterns will emerge. We'll start to understand which types of planets tend to have atmospheres, which ones tend to have stable atmospheres, which atmospheric compositions are common, which ones are rare. We'll start to see the universe not as a collection of individual mysteries, but as a coherent system with patterns and principles. And then, At some point, we'll see something unexpected. We'll see an atmosphere with chemical signatures that biological processes produce. We'll see oxygen or methane or some other biomarker at levels that chemistry alone can't explain. And that will be the moment. The moment we answer the question that humanity has asked for millennia. Are we alone? That moment might come from TRAPPIST-1e, or it might come from another planet entirely. But it's coming. The trajectory of science points toward it. The capability is there. The search is underway. Now, let's talk about one more thing that's important to understand. Let's talk about why red dwarfs matter so much for this whole endeavor. As I mentioned earlier, red dwarfs make up about 80% of all stars in the galaxy. That's not a minor population. That's the dominant stellar type. When you look up at the stars at night, most of what you're seeing are actually red dwarfs. They're just faint, so many of them aren't visible to the naked eye. But statistically, they're everywhere. In a galaxy with 200 billion stars, if 80% are red dwarfs, that's 160 billion red dwarf stars. If each red dwarf has on average a few planets in the habitable zone, that's potentially tens of billions of habitable planets orbiting red dwarfs. That's a staggering number. If even a fraction of those have developed life, then the galaxy is teeming with biology. Tens of billions, maybe more, maybe the number is even higher. But here's where it gets interesting. Red dwarfs have been somewhat neglected in the search for extraterrestrial life. The assumption was that they were too hostile, that their stellar activity would strip away atmospheres, that their radiation would be too intense, that planets around red dwarfs would be sterile. But TRAPPIST-1e is challenging that assumption. If TRAPPIST-1e does have a stable atmosphere, if it has somehow survived despite being pummeled by stellar radiation, then maybe red dwarf planets aren't as hostile as we thought. Maybe habitability around red dwarfs is more common than we assumed. That would completely reshape where we look for life. Instead of focusing on sun-like stars, instead of searching for Earth analogs orbiting stars similar to our sun, we'd be focusing on red dwarf planets. We'd be looking in the most common type of star system in the galaxy. And if that's where life is, if that's where the bulk of the galaxy's biology actually resides, then our entire search strategy might be backwards. We've been looking in one place when the answer has been in another place all along. This is why TRAPPIST-1e is so important, not just for what it tells us about that specific planet, but for what it tells us about the broader universe, about where habitability can exist, about where the galaxy's life might actually reside. If this world is habitable, if its atmosphere is real and stable, then we need to completely reevaluate our models of planetary habitability. We need to revise our understanding of which stellar systems are most likely to harbor life. We need to reprioritize our search. And if it's not habitable, if this turns out to be a false signal or a dead world despite atmospheric signs, then we've also learned something important. We've learned that atmospheres alone don't guarantee habitability. We've learned that there are subtleties we haven't accounted for. We've learned that our models need refinement. Either way we learn, either way the search improves, either way we're moving forward. That's the beautiful thing about science at the frontier. You can't lose. You can only discover. You can only learn. Every result, every observation, every data point contributes to a larger understanding. And right now, TRAPPIST-1e is at the center of that learning process. It's the focus of intense scientific interest. It's the subject of major telescope time. It's driving discussions about the future of exoplanet science. It's shaping the questions we ask about habitability and the location of life in the galaxy. In a few months, as more data comes in, as more observations accumulate, as the analysis deepens, we're going to know so much more about this world. We're going to have a clearer picture. We're going to be closer to understanding what it really is and what it really means. And that process, that slow unveiling of a mystery through careful observation and rigorous analysis, that's what science at its best actually looks like. Let me shift perspective one more time. Let me talk about what this means for you personally, not as an abstract concept, not as interesting science, but as a human being living right now in 2025. Because here's something that's genuinely worth thinking about. You're alive during a specific moment in history. You're alive during the moment when humanity is developing the capability to search for extraterrestrial life seriously. For the first time, we have tools that can actually answer the question of whether life exists elsewhere. That's not nothing. Throughout human history, throughout all of recorded civilization, this question has been purely philosophical. People speculated, people imagined, people built myths and religions and philosophies around it, but nobody could actually test it. Nobody could actually look. Now we can. For the first time ever, we can point a telescope at a distant world and ask whether life exists there. We can analyze the atmosphere. We can look for biosignatures. We can actually search. In 10 or 20 years, maybe less, we're probably going to have an answer. We're probably going to know whether the universe harbors life beyond Earth. We're probably going to cross one of the greatest thresholds in human history, and you're going to witness it. You're going to be alive when it happens. That's remarkable. Think about what that moment will be like. Think about what it will mean. For thousands of years, humans have asked, are we alone? And the answer has always been, we don't know. But one day, probably soon, the answer will change. It will be no, we're not alone. There's life out there, real life on a real world orbiting a real star. That's going to reshape everything: politics, religion, science, philosophy, culture, how we see ourselves, how we understand our place in the cosmos. And it might start with data from a distant planet that nobody had heard of before. TRAPPIST-1e, a world orbiting a red dwarf 40 light-years away, a world that might have an atmosphere, a world that might be habitable, a world where life might be thriving right now. That's extraordinary when you really think about it. That's the kind of thing that only happens once per generation, or once per century, or once in all of human history. So pay attention, stay curious, follow the updates as they come in, because you're watching history being written in real time. Now let me get a bit more practical. Let me talk about what you can actually do with this information, how you can engage with this science. First, understand that science is a process. It's not a moment. It's not a headline. It's a continuous process of observation, analysis, debate, and refinement. The James Webb observations of TRAPPIST-1e are part of that process. They're not the end, they're the beginning. So when you see news about TRAPPIST-1e, context matters. Is this a preliminary finding? Is this a peer-reviewed, published result? Is this a team presenting their findings at a conference? Or is this speculation? Different levels of evidence support different levels of confidence. The current TRAPPIST-1e atmosphere findings are preliminary. They've been presented at conferences. They haven't yet been published in peer-reviewed journals. That's coming. But it hasn't happened yet, so the confidence level should be moderate, not dismissive, but not absolute either. That nuance is important. It's the difference between saying the evidence is compelling and saying the evidence is proven. Compelling means it's worth taking seriously. It means it deserves further investigation. Proven means we're confident. Second, think about how to interpret updates as they come in. If future observations confirm the preliminary findings, if the signal gets stronger with more data, that increases confidence. If future observations contradict the preliminary findings, if the signal disappears or looks different, that decreases confidence. This is normal. This is how science works. Preliminary findings don't always hold up under scrutiny. That's not a failure. That's the system working as intended. Third, engage with multiple perspectives. Not every scientist agrees with every interpretation. There are researchers who are skeptical of the TRAPPIST-1e atmosphere detection. There are researchers who think the signal is real but have different interpretations of what it means. There are researchers who are cautiously optimistic. There are researchers who are cautiously pessimistic. That diversity of opinion is healthy. It's how we avoid groupthink. It's how we catch errors. It's how we converge on truth. So if you're following this story, follow multiple sources. Read skeptics. Read enthusiasts. Read people in the middle. Form your own judgments. Fourth, understand that exoplanet science is moving very rapidly right now. New discoveries are coming constantly. New techniques are being developed. New telescopes are coming online. The field is in rapid expansion. TRAPPIST-1e is one story among many. There's also TRAPPIST-1d, another planet in the same system that might be habitable. There's Proxima Centauri b, orbiting the closest star to our sun. There's a whole catalogue of potentially habitable exoplanets being studied. Each one of these worlds is interesting. Each one could harbor life. Each one could be the world where we eventually detect biosignatures. So pay attention to the broader search, not just to one specific planet. Fifth, think about what you'd want to know if you were going to understand this topic deeply. If you wanted to go beyond just reading headlines and actually understand what's happening, what would you need to learn? You'd want to understand orbital mechanics, how planets move, how tidal locking works, how transits happen. You'd want to understand spectroscopy, how light interacts with matter, how atoms and molecules absorb specific wavelengths. You'd want to understand habitability, what conditions are necessary for life, what we mean by the habitable zone, what kind of atmospheres could support biology. You'd want to understand stellar physics, what red dwarfs are, why they behave differently than sun-like stars, what stellar flares do. You'd want to understand the search for extraterrestrial life, what biosignatures are, how we might detect them, what challenges we face. None of this is impossibly difficult. None of it requires years of specialized training. It's accessible to anyone willing to engage seriously. And the more you understand the underlying science, the more nuanced and sophisticated your engagement with these discoveries becomes. Now let me talk about something that's often overlooked. Let me talk about the international dimension of this work. TRAPPIST-1 itself was discovered through observations made with a telescope in Chile and another telescope in Morocco. The two telescopes are part of the TRAPPIST project, which is a collaboration involving researchers from Belgium, France, Switzerland, Austria, Germany, Spain, and other countries. The James Webb Space Telescope is a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. The technology, expertise, and resources come from multiple countries working together. The DREAMS team that's analyzing the TRAPPIST-1e data includes researchers from multiple institutions and multiple countries. This is typical of modern astronomy. It's collaborative, it's international, it's a genuine global effort to understand the universe. That's important to understand because it means the search for extraterrestrial life isn't a competition. It's not one country trying to beat another. It's scientists from around the world working together toward a common goal. That's actually quite beautiful when you think about it. In a world with so much conflict and division, here's an arena where people are genuinely cooperating, working together, sharing data, building understanding collectively. The discovery of life beyond Earth, whenever and wherever it happens, will be a discovery made by international science. It will belong to all of humanity. It will be a moment of genuine global unity. That matters. That's worth understanding. Now let me address something that I know people sometimes wonder about. If TRAPPIST-1e does turn out to be inhabited, if it does have life, what happens next? Do we send a spacecraft there? Do we try to make contact? Do we try to bring samples back to Earth? The honest answer is, we don't know yet, but we can think through the practical challenges. TRAPPIST-1e is 40 light-years away. That's about 380 trillion kilometers. With current spacecraft technology traveling at the fastest speeds we've ever achieved, it would take hundreds of thousands of years to reach, probably 1,000,000 years or more. That's beyond any practical timescale. We're not sending spacecraft to TRAPPIST-1e anytime soon. We're not making contact. We're not bringing samples back. What we will do is observe. We'll study it with telescopes. We'll analyze the light from its atmosphere. We'll look for signs of life, and from that analysis, we'll learn about whether life exists there and what that tells us about the universe. That might sound limiting compared to visiting another world directly, but it's actually quite remarkable. We can learn a tremendous amount from light alone. We can understand the atmosphere. We can search for biosignatures. We can get a genuine picture of what the world is like. It's not as direct as visiting, but it's possible, it's feasible, it's something we can do now. And perhaps more importantly, understanding life on TRAPPIST-1e through observation prepares us for eventual direct study of other worlds in the future. When we develop faster spacecraft, when we eventually have the capability to travel between stars, we'll have already learned the techniques for studying distant worlds. We'll know what to look for. We'll have a roadmap, but that's centuries or millennia away. What's happening now is observation, analysis, understanding. That's the frontier we're on. Let me bring this back to where we started. Let me remind you of the core question that started this entire investigation. A few weeks ago, the James Webb Space Telescope pointed at a star 40 light-years away. It looked at a planet orbiting that star, and it found signs of an atmosphere, real evidence based on actual data that a distant world has gases surrounding it, gases that might protect life, gases that might represent a stable, habitable environment. And now we're waiting to see if that evidence holds up. Now we're watching science unfold. Now we're in the space between discovery and confirmation. Now we're in the story being written. That's where we are. That's the moment we're living through. And it's genuinely extraordinary, because if this holds up, if TRAPPIST-1e does have a stable atmosphere, if it is genuinely habitable, then we've just discovered that the universe is probably full of habitable worlds. We've discovered that life-supporting conditions are probably common. We've discovered that we're almost certainly not alone. That's a fundamental shift in our understanding of existence. That's the kind of moment that only comes along rarely. And it started with a dim star and a distant planet, and astronomers willing to push a telescope to its limits to answer a profound question. That's the power of science. That's the power of curiosity. That's the power of actually looking at the universe and asking, what's out there? We don't know yet what we're going to find. We don't know if TRAPPIST-1e will turn out to be the world where life is discovered. We don't know if it will be a dead rock after all. We don't know what the universe will show us. But we're looking, and the looking itself, the act of observation, the gathering of data, the pursuit of understanding, that's where the magic happens. That's what we're part of right now. There's something I want to address directly because it comes up a lot when people think about exoplanet science and the search for life. There's a question that sits in the back of people's minds. If we find life on another world, even just microbial life, what does that do to how we understand ourselves? We've already gone through this a few times in history. When Copernicus showed the Earth wasn't the center, that was shocking. It undermined how people saw our place in the universe. When Darwin showed that humans evolved through the same processes as other animals, that was destabilizing. It challenged how we understood ourselves. Each time, we adapted, we moved forward, we incorporated the new understanding into our worldview. Finding life on another world would be another one of those moments. It would be humbling in some ways. It would mean that Earth is not the only place where biology emerged. It would mean that the conditions for life are probably not exceptional, but I'd argue it's actually liberating too, because it means we're part of something. We're part of a universe where biology is natural, where life emerges wherever conditions allow, where consciousness and intelligence are probably normal rather than miraculous. That's profound. That's empowering. That's worth thinking about. Now, here's something else to consider. Once we find evidence of life beyond Earth, even if it's just microbes, that raises the next set of questions. If life exists on multiple worlds, How often does it emerge? Is it common or rare? And then, how often does life become intelligent? How often does it develop technology? How often does it become spacefaring? These are the questions that feed into the Fermi paradox. If life is common, if intelligent life is common, if technological civilization is common, then where is everybody? Why haven't we detected signals? Why haven't we found evidence of other civilizations? There are various hypotheses. Maybe life is common, but intelligent life is rare. Maybe intelligent life develops technology, but that technology is short-lived. Maybe civilizations tend to destroy themselves before they can spread across the stars. Maybe they're all out there, but they're avoiding contact. Maybe we're genuinely unique in our corner of the galaxy. These are profound questions, and they're only going to become more pressing once we've found life beyond Earth. Because then we'll have real data points. We'll know life is possible. We'll know it happened at least twice. We'll be able to start asking about frequency. TRAPPIST-1e might not provide those answers directly. TRAPPIST-1e is probably not home to technological civilization, but it provides data that feeds into the larger question. It tells us something about where life might be. It tells us about the conditions on habitable worlds. It tells us about the prevalence of potentially habitable environments. And from that data, piece by piece, we build a picture. Over time, across many observations of many worlds, we'll start to understand life in the universe. We'll start to answer Fermi's question, not perfectly, probably never with complete certainty, but we'll narrow it down, we'll reduce the mystery. That's the long-term goal. That's the vision that drives much of modern exoplanet science. Now let me talk about something that's actually happening right now that most people don't know about. There are ground-based telescopes that are also looking at TRAPPIST-1e, independent observations, different instruments, different methodologies. One particularly interesting project involves using high-resolution spectroscopy to look for atmospheric gases. Instead of transmission spectroscopy, which is what James Webb does, this technique looks at the spectroscopic signature of reflected light from the planet itself. It's a different approach. It has different strengths and weaknesses compared to transmission spectroscopy. But when you combine data from multiple techniques, you get a more complete picture. You reduce the chances of misinterpretation. You increase confidence in the conclusions. There's also work being done on theoretical models of TRAPPIST-1e, computational simulations of what the planet's atmosphere might be like under various scenarios. These models help interpret observational data. They help predict what we should see if certain conditions are present. And there's analysis of the planet's interior. If TRAPPIST-1e has tidal heating, as we've discussed, what does that imply about the planet's structure? What does it tell us about how hot the interior is? What does it tell us about whether volcanism should be present? All of this work feeds together. Multiple teams, multiple approaches, all converging toward a more complete understanding of this single world. That's how frontier science works. It's not one discovery by one genius. It's collective effort, distributed labor, multiple perspectives combining toward truth. And that work is happening right now. While you're watching this video, while you're reading about TRAPPIST-1e, scientists around the world are analyzing data, running simulations, preparing papers, building the case for what this world is. By the end of 2025, we'll have significantly more information. By 2026, we'll probably have peer-reviewed publications. By 2027 or so, we might have a solid scientific consensus about what TRAPPIST-1e actually is. The uncertainty window is closing, not to zero. We might not be completely certain until we can actually visit the world. But the window is narrowing, the mystery is being solved, the frontier is advancing. Let me shift now to talk about what failure looks like in this context, because I want to be balanced. I want to acknowledge that the TRAPPIST-1e atmosphere detection might not hold up. What if the additional observations don't confirm the signal? What if the spectroscopic signatures are smaller than initially thought? What if the data is consistent with an even thinner atmosphere than we discussed, or even with no atmosphere at all? That's possible. That happens sometimes in science. Preliminary findings don't always hold up. If that happens, what does it mean? It means TRAPPIST-1e is probably not habitable, or at least not habitable in the conventional sense. It might have an extremely thin atmosphere that we can barely detect. It might have a subsurface ocean beneath an icy crust. It might be completely sterile and airless. And from a broader perspective, it would tell us something important about red dwarf planets. It would tell us that maintaining an atmosphere in the face of stellar violence is harder than we thought, that our models of atmospheric erosion underestimated the damage. That's valuable information. That's data that scientists need, because if most red dwarf planets can't maintain atmospheres, then most red dwarf planets probably aren't habitable. And if most stars are red dwarfs and most red dwarf planets aren't habitable, then habitable planets might be rarer than we thought. That would be disappointing in some ways. It would mean the galaxy is less full of life than we hoped, but it would also be important information. It would reshape how we search. It would help us focus on the systems and planets planets that are most likely to harbor life. So even if TRAPPIST-1e turns out to be a false alarm, even if the signal disappears under scrutiny, it's not a failure. It's still a success. It's still part of the search. It's still contributing to our understanding. That's an important mindset to have when following frontier science. The goal isn't to confirm what you hope. The goal is to find truth. And truth sometimes disappoints. Sometimes it's less exciting than the preliminary hints suggested, but it's always more valuable than the alternative, which is to remain in ignorance. Let me also address something practical, the question of scientific literacy and how the public engages with science. There's been a lot of discussion in recent years about misinformation, about how people get confused by conflicting information, about how hard it is to know what to believe when there are so many voices making claims. Exoplanet science is an area where this plays out. There are people who are genuinely excited about TRAPPIST-1e. There are people who are skeptical. There are people who see it as evidence that we're about to make contact with aliens. There are people who think it's much ado about nothing. How do you navigate that? How do you figure out what's actually true? The first step is understanding the sources. Who's making the claim? Are they qualified? Are they an actual scientist working on the research? Or are they a science communicator? Or are they someone on the internet speculating? Different sources have different credibility. A peer-reviewed scientific paper is more reliable than a news article, which is more reliable than a social media post. That's not absolute. There are flawed peer-reviewed papers. There are accurate social media posts. But on average, the more rigorous the vetting process, the more reliable the source. Second, look for consensus. If multiple independent researchers are reaching the same conclusions, that's more reliable than a single researcher making a unique claim. If papers from multiple institutions are saying similar things, that carries more weight than papers from a single group. Third, watch for caveats and uncertainties. Real scientists describe their limitations. They say, this is preliminary, this needs further study, this might not hold up. If someone is making absolute claims with no hedging, that's a red flag. Real science involves uncertainty. Fourth, look at track records. Has this researcher been right before? Have their predictions come true? Or have their previous claims been overturned? That history matters. Fifth, be skeptical of sensationalism. If the headline sounds too good to be true, it probably is. Genuine scientific discoveries are interesting without being sensationalized. If someone needs to exaggerate to make a story compelling, there might be a reason for that. All of this is learnable. You don't need to have a PhD in astrophysics to engage critically with exoplanet science. You just need to be willing to pay attention to the quality of evidence and the credibility of sources. Now let me bring this toward conclusion. Let me talk about what you should actually do with the information in this video. First, stay curious, stay interested, follow this story as it develops. The TRAPPIST-1e data is going to keep coming in. The analysis is going to keep evolving. Updates are going to be published. Watch for them. Second, engage critically. Don't just accept headlines. Don't just believe what sounds exciting. Read the actual science. Look at the data. Think about the logic. Ask questions. Third, share thoughtfully. If you talk to people about TRAPPIST-1e, if you share this information with others, be clear about what we know and what we don't know. Be clear about what's preliminary and what's confirmed. Be honest about uncertainties. Fourth, think deeply about what it would mean. Think about what it would mean if TRAPPIST-1e is habitable. Think about what it would mean if it's not. Think about how either outcome changes our understanding of the universe. Fifth, recognize that you're part of this. You're part of a species that's beginning to understand the universe. You're part of a moment in history where the questions you're asking are actually answerable. You're part of the search. That's significant. That's worth acknowledging. That's worth being grateful for. And sixth, think forward. The future of exoplanet science is going to be extraordinary. Over the next decade and beyond, we're going to detect atmospheres on more and more worlds. We're going to start narrowing down which planets might be habitable. We're going to begin searching for biosignatures in earnest. We're going to move toward actually finding evidence of life. You're going to live through that. You're going to see it happen. That's rare. That's special. That's something to pay attention to. So as we move toward the finale of this video, as we start wrapping up, I want you to hold on to that sense of significance. Hold on to the realization that we're living through a pivotal moment in the history of science, a moment where humanity is beginning to reach out and actually understand distant worlds, a moment where the universe is starting to reveal its secrets. TRAPPIST-1e is just the beginning. It's one data point in a much larger search, but it's an important data point. It's telling us something profound about what's possible. It's showing us that atmospheres can exist on distant rocky worlds, that habitability might be more common than we thought, that the universe might be teeming with worlds worth studying. Whether TRAPPIST-1e itself turns out to be habitable or sterile, the story doesn't end. The search continues, the frontier advances, And we move closer to understanding our place in a universe that's far more complex and far more interesting than we ever imagined. That's what this is really about. That's what TRAPPIST-1e represents. It represents the boundary between what we knew and what we're learning, between speculation and observational science, between wondering and knowing. And we're standing right at that boundary. We're at the moment before the great reveal. We're waiting for the data. We're waiting for the answer. And that waiting, that anticipation, that curiosity driving us forward, that's what makes us human. That's what makes science worth doing. That's what makes this moment so genuinely remarkable. So let me bring everything together. Let me take you back to where we started and show you how the pieces fit into a coherent narrative. We began with a simple fact. The James Webb Space Telescope found evidence of an atmosphere on TRAPPIST-1e, a planet 40 light-years away, a world orbiting a red dwarf star, data suggesting gases surrounding that planet, evidence of something we thought might be impossible. From that one observation, we've built out an entire picture. We've looked at transmission spectroscopy and how it works. We've explored the TRAPPIST-1 system and why this particular planet matters. We've discussed the challenges of maintaining an atmosphere in the face of stellar violence. We've talked about tidal heating and volcanic outgassing, and the mechanisms that might allow a world like this to survive. We've considered multiple possible scenarios: a habitable world with global oceans, a terminator zone with perpetual twilight, a cold, icy planet with a subsurface ocean, each one plausible, each one shaped by the data we have. We've acknowledged the uncertainties, the preliminary nature of the findings, the limitations of our current understanding, the possibilities for error and misinterpretation. We've been honest about what we know and what we don't. And we've situated this one discovery within a much larger context, within the broader search for extraterrestrial life, within the development of new capabilities for studying distant worlds, within the arc of human understanding stretching back centuries and forward into a future we're only beginning to glimpse. All of that flows from one core insight. If TRAPPIST-1e has an atmosphere, if that atmosphere is stable, if it's truly habitable, then everything we thought about the prevalence of habitable planets needs revision. Then the universe is probably far more full of potentially life-bearing worlds than we ever imagined. That's the profound implication. That's why this matters. Now, as we move toward closing, I want to acknowledge something. I want to acknowledge the fact that you've spent over 2 hours of your life watching and listening to this video. That's significant. That's a real investment of your time and attention. I hope it's been worth it. I hope you've learned something. I hope you've gained a deeper understanding of what TRAPPIST-1e is, why it matters, what we might learn from it. But more than that, I hope you've gained a sense of what the frontier of science actually looks like. Not the finished product that gets taught in textbooks, not the polished conclusions that make it into popular magazines, but the actual process, the observation, the analysis, the uncertainty, the gradual movement toward understanding. That's real science. That's what's actually happening right now. And it's happening with this distant planet, this world that we can't visit, this atmosphere that we can only read through light. Let me be specific about what's going to happen next, what the immediate future holds. By the end of 2025, the DREAMS team will have completed their planned observations. 15 additional transits of TRAPPIST-1e will have been analyzed. The dataset will be significantly larger. The signal will be stronger or weaker. The interpretation will be clearer or remain ambiguous. In early 2026, we can expect peer-reviewed publications to start appearing. The team's work will be subjected to scrutiny from the scientific community. Questions will be asked, challenges will be raised, responses will be provided. By mid-2026, there will probably be a growing consensus about what TRAPPIST-1e actually is. Not certainty, but consensus, a general agreement among the scientific community about the most likely interpretation. In parallel, other teams will continue their own work. Ground-based observations will accumulate, theoretical models will be refined, additional data will be collected, and the broader search for atmospheres on exoplanets will continue. Because TRAPPIST-1e is just one world among thousands of potential targets. Once techniques are proven on one world, they get applied to others. The knowledge spreads, the capability expands. Over the next 5 to 10 years, we'll probably have atmospheric analysis for dozens of potentially habitable exoplanets. We'll start to see patterns. We'll start to understand which types of planets tend to have atmospheres and which lose them. We'll start to narrow down the search space for life. And then, probably within the next 15 to 20 years, we'll see atmospheric signatures that strongly suggest biological activity. We'll see oxygen or methane or some other chemical signature that we know life produces. And we'll have our answer. We'll know that life exists beyond Earth. Whether that discovery comes from TRAPPIST-1e specifically, we don't know yet. The data will tell us. But TRAPPIST-1e is definitely in the running. It's definitely one of the most interesting candidates. It's definitely going to be studied intensively. Now, here's something important I want to say directly. The work that's happening with TRAPPIST-1e, the observations, the analysis, the science, that's being done by real people, by researchers who've dedicated their careers to understanding the universe, by teams that have spent years building instruments and developing techniques, by a community that's passionate about discovery. These aren't faceless scientists in white coats in some sterile lab. These are people with families and hobbies and lives outside of science, people who got into this field because they were curious about the universe, people who wanted to understand, people who wanted to find answers to profound questions. The DREAMS team at various universities across Europe, the James Webb Space Telescope scientists at NASA and the European Space Agency, the theorists working on atmospheric models, the engineers maintaining the telescope, all of them, all involved, all contributing. That's worth understanding. That's worth appreciating. Because science isn't just about the results. It's about the people doing the work. It's about the passion and dedication that drives them. It's about the collective effort to move knowledge forward. When you engage with this science, when you follow the updates, when you think about TRAPPIST-1e, you're engaging with the work of real people. You're participating in a global effort to understand the universe. That's meaningful. Now let me talk about what you can do if you want to engage more deeply with this topic, if you want to follow the story beyond this video. First, follow reputable science news sources. Science Daily, Science Alert, Nature News, the Astrophysical Journal. These are places where exoplanet discoveries get covered and discussed with proper context and nuance. Second, learn about transmission spectroscopy. There are excellent resources online, YouTube channels dedicated to astronomy, websites explaining the techniques, books about exoplanet science. Education is freely available if you want it. Third, follow the DREAMS team and other exoplanet research groups on social media. Many researchers share updates about their work on Twitter, Instagram, blogs. You can get information directly from the source. Fourth, think about supporting space agencies and funding for science. NASA, ESA, space agencies around the world, they do this work with public funding. Supporting funding for science means supporting the future of discovery. Fifth, share what you learn. Talk to people about TRAPPIST-1e. Explain what we know. Explain what we don't know. Help other people understand why this matters. Science literacy benefits everyone. And sixth, maintain wonder. Maintain curiosity. Keep asking questions about the universe. Keep being amazed by what we discover. That sense of wonder is the fuel that drives science forward. Now I want to return to something I touched on earlier. I want to talk about what finding life beyond Earth would actually mean, not abstractly, concretely. Right now, as of November 2025, Earth is the only confirmed place in the universe where life exists. We are unique in that regard. Our biology is the only example we have. Our evolutionary history is the only history we know. If we discovered life on TRAPPIST-1e, even if it was just microbial life, that would change everything. We would no longer be unique. We would be part of a category. We would be one of at least two places where life emerged, and the implications would cascade outward. If life emerged twice, independently, then life is probably common. Life is probably what happens when chemistry gets complex. Life is probably natural. Life is probably inevitable, given the right conditions. That means the universe is probably full of it, full of biology, full of organisms and ecosystems and potentially civilizations. The galaxy might teem with life. The universe might be teeming with consciousness. We would move from being alone to being part of something vast, from being exceptional to being typical, from wondering if there's anyone else out there to knowing there is. And once you've crossed that threshold, once you know life is common, your entire perspective shifts. You start asking different questions. Where is the technological civilization? Why haven't we detected them? How many species are out there? What are they like? You move from the question of whether to the questions of how many and what kind. And those are much more interesting questions. But we're not there yet. We don't have that confirmation. We're on the edge of it. We're at the boundary between not knowing and knowing. And we're close, so close you can almost feel it. The data from TRAPPIST-1e is part of closing that gap. The observations coming in are part of the search for the answer. And within your lifetime, probably within the next 15 years, we're going to cross that threshold. We're going to move from speculation to confirmation. And you're going to remember where you were when it happened. You're going to remember that you were paying attention, that you were following the story, that you were part of the search. That's worth thinking about. That's worth being excited about. So as we come toward the end of this video, let me give you the final takeaway. Let me crystallize what this is all about. We live in a universe that's far more complex and far more interesting than any previous generation could have imagined. We have tools that allow us to peer at distant worlds and read their atmospheres. We have the capability to search for life beyond Earth. We have the ability to answer one of humanity's most profound questions. TRAPPIST-1e is one chapter in that story. It's one world being studied. It's one data point in a vast search, but it's an important one. It's telling us something crucial about what's possible, about where life might thrive, about the prevalence of habitable conditions. The story isn't finished yet. The data is still coming in. The analysis is ongoing. The scientific process is unfolding in real time. We're at a moment of genuine uncertainty and possibility. We don't know yet what we're going to find, but we're looking, and the looking itself is remarkable. Over the next few months, as more observations are completed, as more analysis is done, as more data flows in, we're going to understand TRAPPIST-1e better. We're going to get closer to the truth about what this world actually is, and whether it turns out to be a thriving habitable world or a dead rock, whether it supports life or remains forever sterile. We'll learn something important. We'll advance our understanding. We'll move the frontier forward. That's what science does. That's what this moment represents. So my final message to you is this: stay curious, stay engaged, stay skeptical but open-minded. Follow this story as it develops. Think deeply about what it means. Share what you learn. Participate in this moment of discovery, because you're alive during a time when humanity is beginning to truly understand the universe, when we're moving from wondering to knowing, when the cosmos is starting to reveal its secrets. That's extraordinary. That's worth your attention. That's worth your time. The answer to whether we're alone in the universe is coming. It might come from TRAPPIST-1e. It might come from another world, but it's coming, and we're closer than we've ever been. Thank you for spending this time with me exploring this incredible story. Thank you for caring about the universe. Thank you for being part of the search. Now, if you found this valuable, if you've learned something, I'd ask you to do a few things. Subscribe to the channel if you haven't already. Hit the notification bell so you get updates about new videos. Share this with someone else who might find it interesting. Comment below with your thoughts. What do you think TRAPPIST-1e is? Do you think it's habitable? What would it mean if we found life there? These conversations matter. Your engagement matters. The collective curiosity matters, and more broadly, support science, support funding for space exploration, support public education in science. These things matter. They're worth investing in. They're what's going to carry us into the future. Because the future is going to be remarkable. The next decade is going to see discoveries that will reshape how we understand existence. And you're going to be part of it. You're going to live through it. You're going to witness moments that will echo through history. TRAPPIST-1e is the beginning of that story, or maybe just one chapter. But it's real, it's happening, and it matters. Thank you for watching. Thank you for caring about the universe. And thank you for being part of this moment of human discovery. The frontier awaits, and we're moving forward.